All right, welcome everyone to the Climate Variability and Change Working Group. Just a few logistics before we start. So for the speakers, you have 10-minute slots, so try and finish up at 7 minutes, and I or Aisha will give you a wave when you're at the 7-minute mark. We will pay attention to the Slido, so for the people online, if you have questions, please put them there. You need to go to the Slido and then to the center bay of center green. So I'll start our CVCWG update, and I'll hand it over to Aishu in a minute to go through some. All right, so if you're new or you need a reminder, just want to point you towards the Climate Variability and Change Working Group website. This is, I think, a pretty useful resource because we have a list of all the simulations that the working group has produced. And if you go into any one of these, you can find information on how to get the data, whether that be on the CESM machines or through the web access. So I encourage you to go and look there and see what simulations are available. There's also been work by working group members to produce an archive of data, not just from CSM, but from other models. So this multi-model large ensemble archive version 2, so this builds on work that was done by Flavio Lehner with a few years ago, and expands an archive of kind of curated data from large ensembles. So now there's 18 models. They're all kind of regridded onto a common grid, so they'll be much easier for you to use, and 15 2D variables available. And Adam has run all of these large ensembles through the Climate Variability Diagnostics package, and if you go to this website, you can see both the plots from the Climate Variability Diagnostics package, and you can get the information on how to get at the data. So we have a few different simulations in the works, nothing really new for you to look at this point, but things that will be coming, so we'll go through those. So one is the pencil model. So we've been talking about this for quite a while. This is an ocean model within the ocean model hierarchy. So it's kind of between the slab ocean and then the full 3D ocean. So with the slab ocean, you just kind of have a thermodynamic mixed layer. You basically just have the kind of heat capacity influences of having a layer of water there at the surface. And the pencil model is a step up in complexity. It's basically a single column ocean model at every grid point. So you have the mixed layer physics represented. So one of the things you need to do with the slab ocean is prescribe the mixed layer depth. And in this pencil model, you don't have to do that. It's prognostic. And then there are terms that make the large-scale circulation in the ocean be realistic, and there's also a bit of restoring of salinity and upper-level velocities to keep it stable. And so this is a project that's been led by Young-Oh and Gokhan, and it's been in the works for a long time, but it is now running, and Young-Oh has now completed 2 500-year-long pre-industrial controls with this pencil model. They plan to release the data soon, and they plan to also make the pencil model available within CESM2. It has to be within CESM2 because it's using POP, not MOM, which is the ocean model within CSM3. And so if you missed it yesterday, there was a poster by Jiangsu Shin kind of displaying how this model behaves, and here's a figure from that poster where you can see that this pencil model gives you pretty realistic variations in mixed layer depth compared to the fully coupled model, except on the equator where Ekman transport becomes an important part, and I think they're looking into ways of getting that in there. So if you missed the poster, maybe you can see it on the online poster gallery. There's also work going on within the working group on regionally refined configurations. I think this has been a bit delayed just by a lack of capacity for the people that are leading it, but Brian has been working on this regionally refined tropical belt simulation, and I and others have been working on this regionally refined North Atlantic simulation. So just a couple of teasers from these experiments, and hopefully we'll have more details in the coming year or so, but here's an example of the precipitation distribution from Brian in this tropical belt configuration over West Africa, where you can see that the high-res configuration does much better at representing the tails of the precipitation distribution than the low-res. And then in the North Atlantic, the motivation of this experiment was really to look at whether the nature of ocean-atmosphere coupling changes at higher resolution. And here's just a regression of zonal wind onto the AMV index. So basically when you have the positive AMV in the observations, that's accompanied by an equatorward shifting of the jet. This is what the low-res model does. This is an error that, oh yeah, no, they're both CSM2. That's the 1 degree model, and then this is the regionally refined Atlantic. So there are definitely some differences there when you go to this high resolution, and I'm hoping that we can dig into that in more detail in the coming year. There's been work underway to use perturbed parameter ensembles to tune this CAM, including this new machine learning based warm rain microphysics scheme. So this is work from Adisu and Brian. And an example here is just showing this is the monthly precipitation distribution. And you can see that there are improvements in this machine learning based parameterization compared to the original physics-based one that's in the model. So that's ongoing work within the working group. Okay, we have plans for a new ensemble, a single forcing ensemble of CSM2, but using CMIP5 aerosol forcing. I think there's been quite a lot of work that has shown that differences between CMIP5 and CMIP6 aerosol forcings have quite an impact on the historical evolution. And what we wanted to do here is not change our baseline, so use CMIP6 pre-industrial control aerosols and add on the anomalies from CMIP5. So it's not exactly CMIP5 emissions, but it's the time evolution of CMIP5 within a CMIP6 baseline. So this would all be within CSM2. That presented some challenges because at certain points in time the emissions can go negative, and so that's why we haven't started these runs yet. It's taken a bit of time to figure out the emissions. We've decided to kind of take the approach of taking any negatives that happen and kind of pass them out to adjacent grid points. So if anyone has any thoughts on whether that's a reasonable approach or not, I'd be glad to hear before we start these runs. But hopefully we can get these going soon. And I think it would be interesting to do this with CMIP7 emissions as well, as a kind of first look at how the differences in the aerosol emissions change what's happening in the model. So I'm going to hand it over to Aishu now for the last few slides.
All right, first is the TBI experiment. That's a clever quantity experiment. Currently, there's 7 groups participate and using 6 model groups. And most of the model groups have finished the tier 1 experiment. And for tier 2 experiment, CCSM2 has finished by a Chinese group. And right now, there's a protocol paper has published by in GMP recently. So if you want know more details about the TBI experiment, you can look at that paper. And if you want to analyze the data, just contact me. And the other experiment and program is funded in Europe, is focused on tipping point model intercomparison, which is focused, the research is on tipping point, abrupt change, and thresholds. Right now, there's 6 major domains or research focus. NCAR is actively participating in the TipMap ESM, TipMap Ocean, and TipMap Biosphere. And below those is some experimental design. And if you are interested in this kind of experiment, you can contact me. If you want to run some simulation using CESM2, you can also contact me. And the protocol paper is going to publish for each of these domains. And some details you can look at from the website. And yeah, just anything you want to know, just ask me.
All right, yeah, so we don't have a huge amount of time here for discussion, so I just want to encourage you, if you want to kind of get involved in plans for future simulations for the working group, I'd encourage you to join the winter working group meeting where we will have a lot more time to discuss things. Our kind of near-term plans are once CSM3 is available, we start running the various kind of baseline simulations that we do with the working group. That's kind of the immediate plan. Also, if you're not already on the mailing list for CVCWG, please join it, and then you can hear about new experiments or meetings as they happen. So with that, I think we're at the 10-minute mark, so we'll get started with the presentations. And our first speaker is Keja or Melody Liu on land atmosphere feedbacks on heat waves. I'll give you a wave when you're at 7 minutes. Yeah, so it's just this big one. And if you want to use a pointer, just hold that down at the screen, and eventually it shows up.
Good morning, and thank you for having me here. Today, I will going to talk about the importance of how land and atmosphere interactions modulate the surface temperature variance. So here's a brief overview of the presentation. It is well known that climate models are biased in capturing the mid-latitude land surface temperature variance. And in this work, we will demonstrate that the land-atmosphere feedbacks are dominant. And we also found that the atmospheric circulations in synoptic scales aren't as important as previously thought. And we further developed a theoretical framework trying to explain the land-atmosphere feedbacks using the parameters. And then we found that these parameters are actually naturally embedded following the traditional definition of the mixing length. So to start with, we know that the global warming affects the temperature distribution not just by shifting the mean. The changes in the temperature variance will affect how the future warm and cold extreme events will occur. However, the state-of-the-art climate models are having troubles in capturing both the magnitude and the spatial patterns of the temperature variance. And these problems is more severe in the mid-latitude land during winter. So for example, Simpson et al. 2022 paper found that the temperature variance in CSM1 AMIP simulations are way too large compared to the ERA5. And the temperature variance is largely reduced in the preceding CSM versions. And that's largely because the differences between the two different generations of land model. And the newer land model simulates a more conductive snow layers, which will allow a higher surface energy flux exchanges that acts to damp the temperature variabilities. However, we also know that the synoptic scales of weather circulations are quite important. For example, the regional cold spell events are tightly coupled by the upper troposphere blocking events. So there are a few questions that we want to address. First of all, so how important is the synoptic scale atmospheric circulations in addressing these errors? And second, what's the relative role of the interactions between the land and atmosphere? So to address these questions, we run 4 different numerical simulations using CSM2 AMIP type of simulation. To address the first question, we notch the global wind 6 hourly to ERA5 from the bottom to the top of the atmosphere, and we call these experiments as not UV. By comparing the control experiment with not UV, we can determine the relative importance of the circulation. To address the second problems, on top of the wind nodging, we replace the land model from the current version to the preceding version, CLM4, which is employed in CSM1. And we call this simulation as not UV CLM4. We also run another sensitivity experiments without nudging, but replace the land model with the preceding version. So by comparing these 3 sensitive experiments to the control, we can explore the relative contributions from both atmosphere circulations as well as from the land. And here are the results. So in general, we can see that the CSM2 control simulations are weaker compared to the ERA5. And if we look at the changes due to the wind nodgings, we see limited improvement in terms of the temperature variance in the winter. However, if we look at the 2 sensitive experiments where the lands are involved, we do see a significant increase in terms of the temperature variance when the older land model are employed. And these results are broadly consistent with Simpson et al. And so now we sort of know that to address the error questions, that the importance of the synoptic scale atmospheric circulations aren't that important. So from the previous slides, we kind of sense an importance from the processes due to land. But then we wanted to ask, can we derive a more theoretical framework to quantify the role of the land? So here we will start from the tendency equation of the near surface air temperature. From there, we will be able to derive a scaling framework that has a structure shown here. So specifically, the denominators are the parameters that control the feedback strengths of land atmosphere. And we also have the eddy, heat, turbulent heat flux, as well as the temperature gradient acts to fuel the temperature variance. And then we will be comparing our framework to the traditional eddy mixing lengths and to see how they connected with each other. So now let's see how the framework explains our experiments results. Here is also a derivation of the framework. So we start from the simple tendency equations, and then we derive a budget for the temperature variance. And here we perform a variety of parameterizations. Specifically, we parameterize all the dry energy flux using a sensitivity parameter alpha D. And then we parameterize all the terms that are related to latent heat flux with alpha L. Alpha L depends on the soil moisture, evaporative resistance, as well as the background saturated humidity. And then we can derive this following scaling equations. And if you are familiar with the mixing lens framework, that we can see that mixing lens is naturally embedded with the eddy diffusivity as well as these parameters. And now, so let's first look at the relative partitioning between the mixing lens and background temperature gradient. So here we use the smooth potential temperature to calculate the background temperature gradient so that we can minimize the influence from topography. And then we can calculate fractional changes of these equations. So here are the results. The first row shows the fractional changes in temperature variance. And the second row is the contributions from the background temperature gradient that you can see that nothing looks quite similar between the second row and third row. And the third row is the contributions from the mixing length square. And then you can see that the increases in the temperature variance we see in the first row are most likely coming from the contributions from the mixing length. And then we wanted to know what contribute to the patterns of what we see in the mixing length fractional changes. And if our theoretical framework is correct, then the mixing length is a function of both eddy diffusivity as well as these parameters that control the land atmosphere feedback. Here again, we can do the fractional changes with these equations and sort of trying to decompose mixing length into the part that related to eddy diffusivity, as well as the part that encaptures all the feedback strengths. And here again, we have the fractional changes in the mixing length square. And then we can evaluate the left hand of these equations separately here, which is shown in the second row. So the similarity between the second and first rows tells you that the changes in the eddy diffusivity is kind of negligible here. And we can also calculate the parameters independently and evaluate the right-hand side of this equation, which are showing here in the third row. So again, you can see that all three rows look quite similar. So here it tells you two informations. First, that the mixing length is constrained by the land atmosphere feedback. And second, that our framework is quite correct. And lastly, here is a total scaling relationship of the temperature variance. Again, perform fractional changes that we can calculate all each different terms. Here again, we already see the contributions from the interactions between the land atmosphere, as well as the fractional changes in the temperature variance. And the last term is the summation between eddy heat flux as well as the background temperature gradient, as we can see that most of the temperature changes are purely coming from the contributions of the land atmospheric feedback parameters. So a few quick summaries here that we show that correcting the synoptic circulation bias does not address the modal bias in terms of temperature variance. And then we derive a theoretical framework where we can partition the mixing length into the contributions of the land atmosphere feedback. And eventually we know that accurately representing processes involving the land are quite important for the future projections of temperature variance, as a result, the extreme weather events. And I will stop here and taking questions.
Any questions for Melody, either on the Slido or in the room? I'm wondering, so our interpretation was that snow conductivity was just through upward fluxes was damping the temperature variability. Is your interpretation that that is just kind of damping the extent to which circulation anomalies, I guess, how do you kind of relate that to the mixing length?
So basically, if you think of the physical interpretation of mixing length, it's basically how much you can travel before the air parcel can disappear in the background. So that kind of related how much you dissipate energy. So as for the synoptic scale temperature variabilities, usually the advections are acting as the fuel, so it just kind of enhance the variabilities. And from these equations, you do see that this term is in the denominators, and the strengths of this term are always act as the damping. So, and then if here I have a plot of the spatial map of these two parameters. And here, alpha L is much smaller than alpha D, so basically all the dry dampings plays a dominant role here. And that's also kind of consistent with your paper where the snow conductivities and matters, the damping, yeah.
Well, thanks a lot. We'll move on to the next speaker, Prasad Shelke, on lensing through internal variability in heat waves.
Yep. Thanks. Well, good morning. My name is Prasad, and I'm a PhD candidate at Victoria University of Wellington from New Zealand. So far, so south. And this could be potentially my last talk as a grad student, so I'm very much excited for it. This is kind of like a fresh results I'm presenting today, so even like whatever you're seeing, it's something I'm also saying like quite a initial level as well. So let's go through it. So as we all know that 2024 has been regarded as one of the warmest year on record by multiple agencies. Several claims of crossing the 1.5 degrees threshold. All of these are actually coming with a price that we pay in terms of the regional extreme events, such as heat waves, cold waves, precipitation, and whatnot. The major thing about this is some of the regions, some of the remote regions in the world which face actually the unprecedented heat waves, such as this one in Antarctica in March 2022. This actually puzzles me, like, it was a major heat wave event, of course, like caused by atmospheric river and somehow the presence of blocking in Tasman Sea. But if you really see this picture, it's really sad to see ice shelf, which was there for long years, has been collapsing. So this was kind of a motivation for me just to analyze heat waves in the CESM2 large N symbol, which is an integral part of my thesis. So I cannot thank enough NCAR for that. So yeah, approach is simple, just to analyze the heat wave with the classic definition of when the 90th percentile threshold climatology has been crossed by the daily maximum temperature for 3 or more days. We consider that as a heat wave. And I was more interested to see where the natural fluctuations in the system actually causes the variations in the future projections. So I focused more on the signal to noise ratio. Directly on the results, what you're seeing on the left-hand side is actually the northern hemispheric changes, future changes in the heat wave frequency in summer season. The dark spot or dark plot that you see just adjacent to that is a signal to noise ratio at each grid point. And the same you're seeing on the right-hand side. So what you infer from this is even the increase in heat wave frequency in the summer season has been projected to almost similar in the both hemispheres across 18%. There is internal variability that plays a major role, especially in the polar region, Arctic region in northern hemisphere, and somehow in the Southern Ocean as well. So moving forward, I wanted to see, like, whether the trends are matching with when we take the overall mean of the hemispheric heat wave frequency over summer. So that's basically what I've found out, and I'm pretty amazed to see that in the earliest 21st century, Lens 2 actually simulated more heat waves, which is kind of surprising for me. I've also analyzed the cold waves with that, and I get exactly reverse. It's like, in the 20th century, the heat waves, the cold waves were more than anticipated, but in earliest 21st century, they are in in the loop of the observations. So, yep. Overall, what we can see is a stronger trend simulated by Lens 2. And for the southern hemispheric heat wave frequency, it's majorly played by the role of internal variability that says us, like, the natural fluctuations in the southern oceans are pretty dominant over the force trend. So I just wanted to see, like, how the polar regions are showing. I've analyzed pretty much a regional basis as well, but I just wanted to show both poles, how they're showing in terms of the trends. What we can see is for the Arctic summer heat wave trends, they're weaker in Lens 2 than observed based on the NCEP reanalysis too. Over Antarctica, stronger trends, but very high internal variability. Signal to noise ratio is around 0.25, which is very, very high. And Yeah, moving forward, during winter time, surprisingly, the southern hemisphere shows the increase in heat wave frequency by almost 34% compared to the present day simulations. But I feel like it's moreover driven by the internal variability, and I think more of a bias in the Southern Ocean could be a contributor to this. But overall, I've also found out in the next figure, kind of similar what we have seen in the summer season. It's like in the early 21st century, Lens 2 suggested like more heat waves than NCEP reanalysis in the southern hemisphere as well. So as usual, the stronger trends, which was kind of similar finding compared to the summer season as well. Overall, to the Arctic, the trend was closer in here during winter. It's kind of 1.78% per decade in Lens 2 and almost 1.68% per decade in NCEP reanalysis, which was actually surprising for me because the summer trend, summer heat wave trend was much weaker than the NCEP reanalysis. In the southern hemisphere polar region, Antarctica again, the signal to noise ratio was a bit low, and as we can see, there are lots of variability if we see the red line of NCEP reanalysis. Yes, so I think I finished pretty much early in time, but these are, as I said, like these are just initial results of the heat waves, and yep, it's moreover what I can see is like the natural fluctuations plays a dominant role driving the future trends, and I feel there were some of the regions I've seen in the northern hemisphere where force trend actually dominates over internal variability, which suggests that there could be a higher predictability skills. The region surprisingly was around, I think, North Atlantic Ocean, which is a good signal actually. So yep, that's me, and I really want to thank NCAR scientists for bringing the efforts on like building CESM and as awesome it is, and producing more and more simulations, and especially accessible to everyone, especially for someone like me in the Southern Hemisphere. So yep, thank you so much.
Questions? Yep.
In-state bias, and then whether that could contribute to the discrepancy between NCEP and large ensemble.
Yeah, it's a very good question. So actually, like I'll more specifically focus on the southern hemisphere here. So what happens is, like, the heat wave frequency, or let's say any synoptic parameter in the southern hemisphere is actually, let's say, not very well matched between the reanalysis products itself as well. So like expecting that from model is a bit too much. But in the northern hemisphere, there was a less mean state bias. I've not shown it here. I thought I'll go beyond time. So, but yeah, it is a dominant one. Yes, yeah, thanks.
Nice talk, thank you. I'm just curious, it looked like there was a negative heat wave trend in North America for some of those. So any idea what might have caused that in the kind of central part of North America?
Oh, central part of North America is one of my favorite to work on CSM to large ensemble, because I specifically work on blocking as well, and I've seen, like, the blocking associated heat waves during summertime are projected to increase in Lens 2 as well. So I would just say, like, I'm still studying the reasons behind it, but yeah. We'll chat more about it. Thanks.
All right, if there are no more questions, we'll move on to the next speaker. Thank you. So our next speaker is Jairon, and it says virtual in the program, but he made it here. So he's going to talk about human-driven increases in North American and Pacific trough intensifies winter and spring heat waves.
Okay, yeah, thanks so much for the opportunity to talk, and also for the Travel Award that allowed me to be here in person today. This work is under the mentoring of Maria Molina, Kirsten Meyer, Katie Dagon, Ayla Simpson, and John Fasullo. And as Ayla mentioned, I'm going to talk about long-term changes in North American weather regimes, more specifically about the Pacific Trough and the impacts over North American heat extremes during winter and spring.
Sorry, could you move a little closer to the mic?
Yeah,
Thank you.
Sure. So the main motivation is that there is large uncertainty regarding the large-scale circulation and the surface response associated to it. As a result, there are many differences when we compare observations and models in the historical period. And so the tool that I use to address this question or this problem is the concept of weather regimes. And so weather regimes are large-scale atmospheric flow configurations that are persistent and recurrent, and they are useful because they are a way to simplify the representation of the large-scale dynamics, as well as linking those large-scale dynamics with the surface conditions. So the question is, how are the characteristics of these weather regimes changing over the long term? The steps for obtaining the weather regimes are based on geopotential height fields. We compute the anomalies, detrend those fields, and then standardize them. And then we extract the principal components from the fields, the 12 first principal components, and for those 12 time series, we apply k-means clustering to obtain these 5 classes or 5 weather regimes. And then, as I mentioned before, the focus of the talk is the Pacific Trough, which is characterized by this low over the Gulf of Alaska and this high over northern North America. So the increase in frequency that we saw for the Pacific Trough was that it went from 12% daily occurrence to 19% from the past to the present. And when I say the past, I'm referring to the period of 1948 to 1977, compared to present, which is 1994 to 2023. And that increase is significant and large compared to other weather regimes during winter and spring. And so those increases in frequency are important because once we have a Pacific Trough occurrence, we have also anomalies of temperature and precipitation. So we have increased temperature over northern North America, mainly Canada, and we also have dry conditions over the Rocky Mountains and east of the Rocky Mountains. Given those conditions, we also have increased likelihood of some extreme events when the Pacific Trough occurs. So we have increased likelihood of extremely hot days and extremely warm spells, as well as fires, especially over Canada again. As a result of these impacts over the surface weather, when we see an increase in Pacific Trough frequency, that increase is also associated to an increase in some of these extreme events. And so, especially over the region south and west of the Hudson Bay, we see this increase in extremely hot days and extremely warm spells when a Pacific Trough is occurring. And so if we take a more in detail look for the Pacific Trough evolution over time, we see this increase between 1950 and 1990 mainly, and then a decrease after that. And so we have these contradictory signals over time, which are consistent with some literature. On one hand, some papers agree on greenhouse gases deepening the allusion law, which will result in an increased frequency of the Pacific Trough. But there's also this well-documented weakening of the allusion law in the recent years that still needs to be understood, and there are hypotheses linking it to aerosols, for example, or changes in El Niño or La Niña state. So the next question was, how well do models represent this trend, and whether or not, under the model perspective, these changes can be attributed to internal variability or some specific forcing. And so we took a look at 2 large ensembles, CESM2 and E3SM2, and what we saw is that the large ensembles do not represent the trend for the past period. We see that the observed trend or change is outside the range of both ensembles. However, for the future, both ensembles agree on an increasing trend in the Pacific Trough frequency. If we look at the pre-industrial runs, which is the figure on your right, those are the distributions of Pacific Trough frequency differences in all possible periods of the same length as the observed record. And what we see is that the observed differences in reanalysis, which are the vertical lines, lay also outside this distribution of internal variability-driven changes of Pacific Trough. We also looked at the single forcing experiments, and we see that when we look at the ensemble forced only with greenhouse gases, there is an consistent increase in Pacific trough frequency, both for the past and future period. But for the aerosol forcing, there's a decreasing trend. And so what might be happening in the large ensemble is that these two opposing trends can be canceling each other. And then that, that's involved in the representation of these long-term trends. We also looked at the abrupt quadrupling of CO2 simulation, and also compared the last 30 years of the large ensembles to the present. And we saw that under highly increased CO2 conditions, there is consistency with this increase of Pacific trough frequency in both cases. The next question was, what can be the physical drivers modulating these changes? And then what we found is that the trend that goes from 1950 to 1990 might be linked to this cooling in the northern Pacific that happened before that. And then the change inside of the trend might be linked to the La Nina-like warming over the Pacific, which will be consistent with the teleconnections that we know between La Nina and the northern circulation. And so given that, we hypothesized that maybe if we corrected the sea surface temperatures in the models, then we could improve the representation of those trends. However, if we forced the SSTs, here are the Goga and Toga ensembles, we do see an improvement in terms of the increasing trend before 1990 and then the decreasing trend after that for those ensembles. However, the Pacific trough frequency still changes outside the ranges for those two set of simulations. And so this is the summary of the talk. So I showed you that the Pacific trough frequency has increased significantly over the last 80 years or so. And then according to the models, this is likely outside internal variability, and under the model's perspective, it can be driven due to greenhouse gases. Then since we have this La Nina-like warming trend in the recent past, once an El Nino-like state happened potentially in the future, then we potentially will have also an increase in Pacific trough frequency after that, and the subsequent heat extremes or heat conditions associated to it. More research is needed on the role of aerosols and basically try to explain those opposing trends between greenhouse gases and aerosols in the large ensembles. And another question we have is that we want to look at the high resolution simulations to see whether or not we improved the representation of those trends using those high resolution simulations. And that's it. Thanks so much again.
Thank you. Any questions for Jairon? I'm also looking at the Slido if anyone online wants to ask one.
Thanks. Yeah. Nice talk. I was wondering if you have any thoughts on whether the aerosol and greenhouse gas response in CSM are like of the right magnitude. Of course, we don't know them in reality, but since you kind of like point out there's an offset in the model, but that might not be the case in reality. Just wondering.
Yeah, one hypothesis that I have is that maybe the response to aerosols is too strong in the models, and so we see that strong decrease. But again, we try to look at that from the reanalysis point of view, but there's very limited data sets and record to actually assess that. And then, yeah, so potentially maybe the role of aerosols and the magnitude of the role of aerosols is not very well represented, but also it might be that the greenhouse gas is right for the wrong reasons, right? So maybe, it's still an open, hard to assess.
Yep, Aishu. Go up to the mic.
The aerosol forcing change, maybe you can look at the CESM1 large ensemble, which we have a different aerosols, and you may see something similar as ER file.
Okay,
it's possible.
Yeah. Perfect, thank you. I have more homework. Yeah, thanks.
All right, thanks very much. Our next speaker is Jonah Shaw on the emergence of regional warming.
Hi, my name is Jonah. I'm a graduate student, or I guess I just defended my PhD at CU with Jennifer Kay. And today I'll be talking about detecting regional warming, and specifically making that detection as robust as possible while accounting for several different sources of uncertainty. And just to try and motivate this, this is a figure from the most recent IPCC report indicating the year in which these kind of standard IPCC regions are kind of have a detectable change in surface temperature. And I think the reason we're interested in this question is because climate change is fundamentally this regional process, and adaptation and mitigation is also needs to be regionally informed. And so if we really kind of take this figure at face value, you might ask why I'm interested in detecting these changes, because all of these regions have a color associated with them, and they're actually all detectable by 2012. But actually, this is just the top figure of a two-panel figure, and the second panel repeats the same exact analysis, but with a different data set. And so I think just this kind of interchanging your data sets and getting really different answers tells us that there is something going on, that we should be appreciating the uncertainty in our observations when we're asking this question. And so the research questions I'm going to try and answer here are, where actually are these changes robustly detectable when we're kind of accounting for a lot of different sources of uncertainty? And also, how do these different sources of uncertainty, both observational uncertainty and model uncertainty, what are the spatial patterns? How do they influence our regional warming? And just to start, there's kind of some previous literature that does detection of the forced response. We are not doing that. We're working with these historical trends because we're interested in kind of the impacts, which requires us to look at the, observe the historical change in both kind of the influence of the forced change and whatever internal variability realization we've seen. And so how we're going to do this is that we're going to first quantify our historical uncertainty and our surface temperature. And I think normally we think about surface temperature, historical surface temperature, in this very deterministic sense. This is just kind of an annual time series of one of those IPCC regions. Our temperature goes up and down, and there's this kind of long-term warming trend. But really, I think it's better to think about it in a more probabilistic sense, because our records are imperfect. We're not observing everywhere at every time, and we can have biases based on where our instruments are located, and all sorts of other biases that we should account for. And so this kind of probabilistic record is actually just 200 different realizations of historical surface temperature that are all reconstructed from those kind of point observations that are made while accounting for these questions of spatial and temporal representativeness and potential biases in those observations. And we get this record from the NASA GISTEMP dataset. This was developed by Nathan Lenson at Colorado School of Mines and also NCAR. And effectively, our deterministic dataset is just the median of these 200 ensemble members. And so this is a really excellent tool for assessing the role of observational uncertainty in our results. And I think a big takeaway is, whether you're interested in time or emergence or not, these datasets are a really simple and effective way to assess the role of that uncertainty. And so now we're kind of moving on to this question of detection or time of emergence. And so effectively, we take each of these time series, start with 3 years, compute a best or a linear fit to get our trend, add to our 4th year, recompute our trends, and see how they evolve in time. And that's what we're looking at in these kind of red and blue lines. They all correspond to those time series in the left here. In order to kind of assess if these trends are significant, we need to have some understanding of what internal climate variability is, or what kind of trends are expected in the absence of the human influence. And this is this gray envelope here, and we compute it from the CSM1 large ensemble. And so effectively we're just, or sorry, not the large ensemble, but rather the pre-industrial control simulation. So effectively, we're able to resample time periods of the same length many, many times from that 1800-year pre-industrial control simulation, and then explicitly construct a 95% confidence interval to, again, understand what is precedented in the absence of the human influence. And so we can now kind of answer our question of time of emergence, which is abbreviated here by TOE. And so our median time of emergence is this kind of standard method where we ignore this uncertainty in our historical records, and we now define a more strict time of emergence where we require all, or 95% of these different 200 ensemble members to emerge from our internal climate variability. And so we can take this and apply it to all these different IPCC regions and kind of reconstruct a similar figure to what I showed from the IPCC at the beginning. And we can see that, when we just ignore our observational uncertainty, we have some pattern of detectability. And what we're adding here is this strict time of emergence and then the difference between the two, which is just the delay that is imparted by this observational uncertainty. And so effectively what we see when we look at this delay is that there are plenty of regions where that delay is on the order of 0 to 5 years. It's not very large, but there are also regions where the delay is much larger, in excess of 20 or 25 years. So clearly accounting for observational uncertainty is important here if it's making kind of multi-decadal changes in the results of our research question. Of course, I also said that we would be looking at kind of the climate processes that are responsible for these delays. And so I'm just going to show two representative regions to kind of get a sense of what's going on here. And so this first region is West and Central Europe, which is kind of boring. And so we say that it's really characterized by low uncertainty and monotonic trends. Our median kind of deterministic member is really tightly bounded by the ensemble. There isn't a lot of uncertainty. And also these trends do not have a lot of kind of decadal patterns in them. They're pretty flat, they're increasing, and once they all pop out of this kind of envelope of internal variability, they stay out. And so this is a really simple situation in which we can assess this detectability question. If we look at another region, this is the Southeast Africa IPCC region, we have a pretty different story. Not only do we have much higher observational uncertainty, but we also have this decadal patterns in our trends. Specifically, we have this kind of local maximum in our trends around the middle of the 20th century, and then it falls off before increasing again. And so if we just look at all of these kinds of different ensemble members, some of them are detectable, in the mid-20th century, while others are not, and that's really kind of modulated by the presence of these decadal trends. And whether that's internal variability or things like global dimming, global cooling, we haven't looked at it, but the kind of conclusions that we want to draw here are that these non-monotonic warming trends, specifically at low frequencies, and differences in observational quality are really causing the greatest delays in our time of emergence. I also said that I would look at other sources of uncertainty in addition to model uncertainty. And so what we do is we repeat our analysis with an additional 3 Earth system models. So now we're using 4 system models, and we add another observational uncertainty product that also has 200 ensemble members. And so if you mix and match all of these kind of realizations of our historical climate and internal variability, you can generate 1,600 estimates of time of emergence for each region that you're interested in. And just to make a point about these Earth system models, we're not using all CMIP5 or all CMIP6 models. We're specifically using models with large ensembles that have been tested as good, having good regional internal climate variability. So I think it's important to not throw all of our models at this problem, but specifically use the ones that are validated for it. And so now, if we kind of show this plot of median, strict, and total time of emergence, where our delay here is not just due to observational uncertainty, it's due to all of these different sources of uncertainty that we've combined in this kind of new, larger ensemble. And so we effectively see that our delays are much larger, and they've shifted largely towards being in excess of 1, 2, if not more decades. And so all of these sources of uncertainty are clearly really important to account for when answering this question. We repeat our analysis. So our conclusion is that still, despite accounting for all these sources of uncertainty, we're still able to detect warming over in all these regions except for the Antarctic regions. And so I think we're just kind of like playing with this result of uncertainty is really important to account for, but still we're able to detect this regional change when accounting for it. Finally, we repeat our analysis at a much kind of the finer scale that our observational products are available at. And I think this really helps us localize where the delays are, which is largely in South America and sub-Saharan Africa. And I think this really points to the historical way that we observe and kind of aggregate and trust our climate data. Like this is the global South, and this is the impact of our science not being equal around the globe. And it also shows that our trend emergence is just later and less confident at these finer spatial scales. So to summarize, this kind of emergence of regional warming is robust despite accounting for these different sources of uncertainty. And our delays are large. More than 50% of the land surface had emerged by the year 2000, but more than 35% of the land surface is delayed by more than 20 years. And actually, this is now accepted in ERL, so hopefully it will be available in a DOI soon. I'm happy to take any questions. Thank you.
All right, thanks. We are at 10 minutes, so I think we'll skip questions and encourage you to ask them of Jonah in the break. We'll move on to our next speaker. That's Yanning Kuo, and that's about the role of anthropogenic aerosols and ocean warming in driving southwestern U.S. drought.
Hi, my name is Yanning Kuo. I'm a fourth-year PhD candidate working with Flavia Liner at Cornell University. Today I'm going to talk about our finding anthropogenic aerosols and ocean warming are both contributors to the southwestern U.S. drought since 1980 through precipitation changes. So our definition, in our study, the definition of southwestern United States is the box over there from California to Colorado and New Mexico. This is where the Colorado River, the main stream flow through and providing fresh water for the residents over this region. And in the past, since 1980 to 2014, the main precipitation season in DJF MAM, winter and spring, there has been an observed precipitation decline over the southwest, and it is corresponding to the increasing sea level pressure over the Aleutian Low region, where we show as the red contour lines over the North Pacific. And the precipitation decline for this region specifically has created a lot of social and economic impact. For example, naturally that can create more wildfire frequency in the summer, and this region is heavily with agricultural activities, so that also impact agricultural economic. And so this region, the declining precipitation has been attributed to the tropical decadal La Nina-like SST trend, where there's a well-established teleconnection pattern that when you have a cooling trend over the central part of the Pacific, you expect the Aleutian low to be weakened with an increasing sea level pressure trend. And there has been some study that link the aerosols to contribute the La Nina-like cooling trend since 1980. For example, the paper from Yanting Huang. And we also have a paper that link the trend of La Nina-like SST from aerosols to the southwestern US precipitation drying. But today, I'm focusing on the teleconnection. Basically, in observation, we can link, we can explain this circulation chain and precipitation chain with the La Nina-like teleconnection. And so we usually use CESM2 large ensemble or other climate model large ensemble to look at the force response for the same period. And this is probably not surprising to the audience that CSM or a lot of symmetric climate model indicate the historical forced SST is an El Nino-like trend pattern. But what surprises us is that even you have a forced El Nino-like SST trend, your North Pacific circulation and the precipitation for the Southwest indicate a more La Nina-like circulation pattern. So the teleconnection explanation in observation is not valid in the fully coupled climate model force response. And so we take a look at the pre-industrial control simulation, where we have a very long record, and then we can identify the decadal transition that with a strongest El Nino-like SST trend. So we do a composite analysis for that. And we see that in pre-industrial climate, when you have an El Nino-like warming pattern, you have a deepening of Aleutian low with increasing precipitation for the Southwest. If we do the same thing for the historical simulation, we identify the strongest ensemble members with the strongest El Nino-like transition. We can see that overall the tropical SST is warmer compared to pre-industrial control simulation. And for the North Pacific, what's consistent is that there is a missing typical El Nino-like teleconnection over the North Pacific. And so we run Amy pipe experiment with an El Nino-like SST trend. We use a linear inverse model to generate synthetic sea surface temperature and then prescribe the synthetic SST that with an El Nino-like SST trend with the radiative forcings to run Amy pipe experiment. And so in this experiment, we showed that there's a consistent missing El Nino-like teleconnection with the post-1980 radiative forcing, even if you have an El Nino-like SST trend. And so with the AMIP-type experiment, we can now easily decompose the contributor. Basically, we run 2 additional experiments, one with the radiative forcing, and then the SST is the repeated seasonal cycle without any trend. And so in this experiment, we identify the North Pacific, and the northern part of North Pacific, especially in the Aleutian, northern part of Aleutian Island, we have an increasing sea level pressure trend. And we compare that with the CSN2 single forcing large ensemble, the aerosol-only simulation. We identify anthropogenic aerosol as the main driver for the northern part of North Pacific circulation change. And this is independent from the SST. And so we move on to the next experiment we ran. This is an experiment that we prescribed only the El Nino-like SST trend without radiative forcing changes. In this simulation, we can still see there's an El Nino-like teleconnection, but it's much weaker than our expectation from the pre-industrial control simulation. And so the El Nino-like SST trend with the uniform warming in the tropics became less effective when we compare to the pre-industrial climate. And finally, we examine whether the 2 drivers, radiative forcings and the El Nino-like trend with uniform warming in the tropics, is linearly additive to when they prescribe together. And we found that in Chem 6, this model specifically, there's a very strong residual, or we call it as nonlinearity, that when we have radiative forcing and the El Nino-like SST trend together, it generates a stronger anticyclonic response over the North Pacific, and that prevents the precipitation to arrive in the southwestern US in winter and spring seasons. And I couldn't go into too much detail about the mechanism here, but in our paper, we found that this is because aerosol and SST, they create 2 distinct circulation change over the North Pacific, and when they have their distinct changes in the upper level jet stream, that further create a barotropic response for this circulation change in the residual plot. And so in summary, the results of this paper, of this project has been accepted to be published, and I think that will be online soon. But the main takeaway from this presentation is that we show anthropogenic aerosols and the mean tropical warming combined together. They increased the North Pacific sea level pressure so that the southwestern US precipitation declined. And the implication from this study is that the post-1980 southwestern US drought, from the precipitation perspective, might be more inevitable than we previously thought. And I will be happy to take a question.
Any questions for Yaning? On the Slido, I'm also looking at that. Yes, I'm wondering, do you have any thoughts on what aspect of the mean warming is changing the teleconnection from El Nino-like SSTs?
I think from our paper, I think we demonstrate that the mean tropical warming kind of increased the static stability, especially for the subtropical high region, and so that also bring another layer of contributing to the drying over the southwest.
Yep, Jaron?
Do you have any insight into the regional effects of aerosols? Like, are they more important in some region? I know you mentioned some changes in the circulation, like in the Pacific, but yeah, what's more important, North America or Asia, or how do you think about that?
Okay, that's a good question. We didn't do a specific analysis for this study about which regional emission is contributing to this circulation change, but there are some papers, and also one of our previous work, we try to do some analysis on which regional emissions are. We correlate the AOD to the SST, La Nina-like SST due to aerosol, and we identify there's a shift mode. Basically, when your aerosol emission decrease over North America and Europe, and your aerosol emission increase over Asia, that specific mode contribute to the La Nina like SST in the Pacific and also the circulation over the North Pacific. But we didn't do the analysis here. Thank you.
Thank you very much. We'll move on to the next speaker, and that's Paul Curtis about equilibrium climate sensitivity in extra long CESM simulations.
All right. Okay. All right. Good morning, everybody. I'm Paul Curtis. I'm a fourth-year PhD student working with Alexei Fedorov at Yale. And today I'm going to talk about a pretty short and simple study that we did on ECS. And this is in collaboration with Nicole Feldl at UC Santa Cruz. So first, what is ECS? So by ECS, we mean the global mean temperature change once a climate has equilibrated to a doubling of atmospheric CO2 concentrations. Recent assessments, such as the IPCC report, which is shown below, and the Sherwood 2020 paper, put the likely bound of ECS between about 2.5 degrees C on the lower end and about 4 degrees C on the higher end. But really, I want to draw your attention to the CMIP6 band there. And obviously, there's a very big spread in ECS within CMIP6 models, with the lower end being about 1.8 degrees C, and some models with a very high ECS around about 5.5 to almost 6 degrees C. So there are a lot of reasons for this spread, but one of the major uncertainties is that these are based on estimates of ECS, and overall, we really have this lack of simulations which are actually run to equilibrium. So one way to get ECS from a climate model is to do an abrupt n times CO2 experiment and run it out towards equilibrium. So these were collected as part of the long-run MIP group. The simulations are shown below. And basically the trend is that for stronger initial CO2 forcing, you see a higher delta T EQ over C. So for example, taking CESM 104 on the left-hand side there, we see that for a doubling of CO2, you get a warming of about 2.6 degrees C, whereas for a 4 times CO2 experiment, once it's normalized, you get just over 3. So it's higher for larger C. But most of the models here were run for about 1,000 years, so it still begs the question, are we running the models for long enough? So in the first part of my PhD, I did a series of n times CO2 experiments using CSM1. So it's quite old, it's CSM 1.0.4. In the atmosphere, it's CAM4 T31 spectral truncation, which corresponds to about 3.75 degrees, so pretty coarse. In the oceans, POP2, so about ½ degree at the equator and about 3 degrees elsewhere. But the main advantage is that it is relatively cheap to run, and so I've run this model now for just over 80,000 years of simulation time. And today I'm going to focus on 8 experiments, which are shown in the table below. So starting at the warmest, so 16 times CO2, and then we have 8 times 4 down to 2 times CO2, 6,500 year control run, and then 3 global cooling simulations too. And just to really emphasize that we are going out to very long timescales here, so 8 times CO2 is about 10,000 years long. So the main advantage is that we have long timescales, and we're also systematically considering global cooling in our model, which is very rarely done. And just to emphasize that, to our knowledge, these are the longest n times CO2 experiments ever used to compute ECS in a climate model. So first we could ask, well, what happened if we stopped integrating the model after 1,000 years? Well, our ECS curve would look a little bit like this. And there are 2 trends to point out here. So looking at global warming experiments, as we move from 2 times to 16 times, what we find is that the normalized warming per doubling of CO2 gradually increases. So this is pretty much what we saw in long-run MIP. And similarly, going colder for stronger initial radiative forcing, we actually see more cooling for the strongest cases. As we go out to 2,000 years, the trends haven't really changed, but I want to point out that there is a non-negligible amount of warming or cooling in both of these warming experiments and cooling experiments. But is 2,000 years enough? Well, no, it's not the full picture. So what happens when we get all the way out to equilibrium, so this is the last 10% of our experiments, then what we find is that actually the ECS, so properly now ECS, is essentially constant for 5 of the experiments. So between 0.71 and 16 times CO2, we have this near constant ECS of about 3.4 to 3.5 degrees C. And it's only in the coldest experiments that we really see a much higher ECS, around about 4.2 to 4.4 degrees C. So I said a lot of the estimates of ECS are based on something called effective climate sensitivity. So this just really starts by thinking about simple energy balance. So N, top of the atmosphere relative imbalance, is equal to the initial forcing plus the climate sensitivity parameter multiplied by the temperature change. And what we generally do is we take an interval like I've done here with the squares, triangles, and circles, and extrapolate the linear trend back down to n equals 0, which gives us our estimate of delta TEQ. So what we find is that for the strongest forced experiments, so 16 times CO2 and 8 times CO2, as long as we're not taking the first 1 to 10 years, actually effective climate sensitivity does a pretty good job of getting the realized equilibrium warming. But as we get colder and colder, we find, and especially in the very coldest experiment, that effective climate sensitivity misses ECS almost completely. So you can look at the coldest one there and see that if we try to estimate the equilibrium cooling using years 300 to 600, then we'd get about 6 degrees C. But the reality was about 4.2. So the variation in lambda, so the climate sensitivity parameter, this is due to changes in shortwave feedbacks. In global warming experiments, this is predominantly due to shortwave cloud feedbacks. And in global cooling scenarios, this is predominantly due to clear sky feedbacks, and in particular albedo feedbacks. This is mainly due to the strong expansion of sea ice into the North Atlantic and the North Pacific, as well as the enhanced snow cover over the land. So to leave you with a summary and some conclusions, so within these experiments of CESM1, we've determined an almost constant ECS of about 3.43 degrees C across a wide range of climates. These correspond to global mean surface temperatures at equilibrium between about 285 and 300 kelvins. And really the main implication is that once we get to the very long timescales, this ratio of delta TEQ over C doesn't necessarily increase for higher C, which is a big result in our opinion, and this is something that really takes multiple thousands of years to emerge in the model. And so really when we're dealing with ECS, we should be running the models for as long as possible, and it also helps to consider global cooling to really have a systematic analysis between cases. And so I'm happy to take any questions. Thanks.
Any questions for Paul? Oh, yeah, go.
This nonlinear behaviors across various degrees of CO2 forcing. I was wondering if you have looked at the role of radiative forcing instead of feedback to set the nonlinear behaviors across the CO2 levels.
So would this be looking at F?
Yes.
Yeah. So I think if I go back, can I go back? So there's a few studies that I think talk about F increasing. So as you increase the amount of CO2, then F gets stronger. So if you look at a curve like this, then one conclusion could be that actually the climate sensitivity is decreasing, right? In a way. We didn't look into this too closely. Our point was just to really actually look at what the equilibrium warming is. Yeah.
Right.
CAM4 physics, which uses an old radiation scheme that's somewhat flawed.
Sure.
And I'm wondering if your results might be sensitive to that, or at least the timescale that you're finding might be sensitive to that, especially if you might be saturating the water vapor bands.
Oh, so I think with regards to saturating the water vapor bands, I don't know if that would happen at 300 kelvins. It might be a little bit too cold for that. I think that typically happens around 305, 310 in some of the models. With the specific scheme in CAM4, I'm not too sure. I think that was something we would need to look into a little bit more. But yeah.
Questions? Yeah, Aishu.
My question is, in this simulation, you do not consider the change of the ice sheet. So when you consider the cooling, you see reduce the CO2, and you can have the CS albedo effect and also snow effect.
Yeah.
But for the warming, if you consider the melting of the ice sheet, do you think the equilibrium sensitivity will change? Could it match your cooling?
That's a really good question, actually. I'm not sure. We can talk afterwards, perhaps. Yeah. Yeah.
All right.
Okay.
Thanks very much.
Thank you.
Okay, our next speaker is Jacob Stuyvenant Allen on the role of atmospheric nonlinearities in producing ENSO asymmetry within a statistical dynamical version of CESM.
Wow, this is a very loud stage. Hello, everyone. I'm Jacob. I'm a new project scientist over at NCAR-RAL, but this is some work I did during my postdoc with Alexei Fedorov, so same guy from the last talk. How do I go next? There we go. Okay, so ENSO in observations, we typically look at a map like this, which is showing us a linear view of SST anomalies, simply a regression of those SST anomalies onto the Niño 3.4 index. But what this hides is that El Niño and La Niña are not mirror images of each other. And one of the ways in which they're different is in their magnitudes. So if I draw a couple of lines across the Niño 3.4 index in observations, you can see that El Niño events tend to be larger in magnitude than La Niña. And this results in a skewness of about 0.5 since 1980. Another way that they're different is in their spatial patterns. So El Niño tends to be shifted a bit further to the east, while La Niña is kind of centered in the middle of the basin. And there's some variation here, but generally speaking, these are the features we can observe in SST. And I want to highlight just in terms of the linear dynamics, right? Wind anomalies are really important for moving warm or cold water throughout the basin, specifically zonal wind anomalies. And the way that they're doing that as well is that the thermocline is adjusting to those processes. So this is very hand-wavy and linear, but functionally what I want to highlight is that one of those processes, either in the atmosphere or ocean, has to account for the difference that we're seeing in El Niño versus La Niña amplitudes and spatial patterns. And in the literature, people will talk about westerly wind bursts or maybe the role of the nonlinear response of wind stress to SST. And in the ocean, people point to the role of nonlinear heat advection and essentially processes that result in the thermocline adjustment being different for El Niño versus La Niña. And this is a bit of the academic chicken or egg, but I think it is important because if you look at GCMs and CMIP6, for example, the range of skewness is minus 0.5, meaning La Niña is way stronger than El Niño, all the way to 1.15. And CSM2 in particular, for the 1,000-year PI control, has a negative skewness as well, minus 0.2. So this is not something that models are picking up well. I'm going to skip that one. So what we do is we take CSM2 and we design an experiment that allows us to essentially manipulate the characteristics of zonal wind stress within the fully coupled model. And this is commonly called a hybrid coupled model of ENSO. There's a few examples out there. But what we do is we take wind stress anomalies from reanalysis, so they're coming from ERA 5, and those are estimated with simple statistical methods. And we keep the climatology from the CSM2 control. We edit the source code in the coupler, so we're manipulating zonal momentum flux. When the atmosphere is communicating that momentum flux to the ocean, we intervene and say, no, please use the pattern that we are prescribing rather than what you would normally do. In a simple formulaic expansion, you could think of this as a first-order polynomial where your wind stress in the tropical Pacific is equal to a 365-day climatology from the PI control with this additional linear term, which is just the anomaly of wind stress multiplied by the internal Niño 3.4 index. So it evolves freely within the model. And then you can just add a second-order term, so quite simple. And the second-order term is proportional to the square, right, of the Niño 3.4 index internal in the model. Let's take a look at what that looks like in space. So this is an animation showing us the wind stress that we're prescribing in the model. Blue is easterly and red is westerly. So as the Niño 3.4 index becomes more positive, what you see is just an increase in the magnitude of westerly wind anomalies. As it switches back to La Niña, you'll see that the spatial pattern is exactly the same. So those are they're perfectly symmetrical with each other, perfectly linear. Now, if you want to add in a nonlinearity, you can simply do a second order fit on these grid point values. And notice as we switch from La Niña-like conditions all the way to El Niño, that not only do we have different patterns and magnitudes of wind stress, but they evolve in time based off of the magnitude of the Niño 3.4. So these westerly wind anomalies are actually shifting east in the model and more appropriately replicating the actual processes that happen in reanalysis and observations. Okay, so that's our hybrid couple experiment. We run 4 simulations, 2 linear ones. Basically, we modify the strength of the wind stress in the model and we look at how ENSO responds. And then we run 2 nonlinear simulations as well, where we add in that nonlinear term, and again, we just modify the strength of it. So I'll talk about why we do that. The linear simulation alone can tell us, okay, in the absence of atmospheric nonlinearities, what is the asymmetry that the ocean model produces completely by itself? Without this nonlinear feedback and wind stress, what does the ocean do? Then we can ask the question, do ocean nonlinearities depend on the strength of that atmospheric forcing in a linear framework? The nonlinear experiments will then basically tell us, okay, what's the importance of this nonlinear atmospheric wind stress feedback to underlying SST anomalies? All right, let's look at some results finally. This is just a time series of the Nino 3.4 index. We run this for 200 years. And what we see here is actually really good in terms of ENSO and really good in terms of a hybrid coupled model. So we have the nice characteristic 2.7 to 5 year dominant variability of El Nino and La Nina events. There's irregular and chaotic behavior. If you've seen other hybrid coupled models, they're completely cyclical, whereas this one, because we leave all the other fluxes allowed to freely do what they do, we get quite a nice and chaotic El Nino. And it also gives us realistic amplitudes and spatial patterns. So all in all, I was feeling pretty happy after we ran this first experiment. But note that in the bottom left, you can see that the skewness of this experiment, it results in an ENSO that is negatively skewed. Again, La Nina is stronger than El Nino. When we increase the coupling strength, or just make the wind stress stronger, this gets worse. So the ocean actually produces a negative asymmetry in ENSO without these appropriate atmospheric nonlinearities. When you start to add those in, then we get things that look a lot more like observations. So if you look at kind of the -2 degree C line, our La Nina amplitudes are drastically reduced, and we're getting strong El Ninos, much like we observe in observations. And the skewness here is about 0.2, but only by adding the full nonlinear term can we get statistics which look exactly like we see in observations. So this is really highlighting that the atmosphere is the critical driver of creating this fundamental asymmetry in ENSO. Here I just want to show, let's see, oh yeah, this got updated. So I'm not going to talk too much about these pictures, but a lot of other work has showed that ocean nonlinearities are important as well. And what I want to draw your attention to, if you look at the red shading, the bottom 2 panels are our nonlinear experiments. And what we're showing is basically nonlinearities in the ocean only arise when you have the appropriate atmospheric nonlinearity. So in the chicken or egg question, the atmosphere is really driving this feature that we see in good performing climate models and in reanalysis. So can ocean nonlinearities alone create asymmetry? Well, not the correct one. Without the wind stress nonlinearities, ENSO is actually negatively skewed. Do ocean nonlinearities depend on coupling strength? Actually, this exacerbates the problem. So if you just add more momentum flux into the model, you're going to make your ENSO technically worse. But if you add in the appropriate nonlinearities, this is when you start to get an ENSO that behaves much like what we see in reanalysis and observations. So I'll leave, if I can go back one, yeah. I'll leave my conclusions up here, but what I want to highlight as well for CESM3 is that there's a problem with the El Nino to La Nina-like phase transition. These are just some Hofmüllers, and what you can see is in the linear case on the left, you have a El Nino event which exists for almost 2 years. You have anomalies which persist throughout the tropical Pacific. And with the nonlinearities, part of this paper that I just submitted, so fingers crossed, but part of what we show as well is that the actual transition gets a lot better when you have the appropriate atmospheric nonlinearities. So some of those problems might come from not prescribing or not having the correct response to tropical convection and wind stress anomalies within this tropical Pacific. So I'll end there. Thank you, and I'll take any questions.
Thank you. Any questions? I guess I have a question. So it seems like you'd need to run a long time to really know the true nonlinearity. Do you have kind of like a key diagnostic you would recommend, like some nonlinear regression onto Nino 3.4 or something for model evaluation?
Yeah, I think Andrew Wittenberg, I think came out with a paper that said you need 200 years of ENSO statistics to trust them. But in our simulations with CSM, it was actually quite stable. I would be checking results 50 years, 70 years, 100 years. And I didn't find that it changed that much. So maybe that's a bit good in terms of like model development for ENSO. Did that answer your question?
So I guess I was thinking of, rather than just kind of measuring the nonlinearity, if you had, say, a 30-year run, would you recommend like regressing wind stress in a particular region onto Nino 3.4 to see whether you're kind of capturing the processes that are relevant?
Yeah, you can do that and do a second order polynomial fit as well. So you'll get a second term, and you could compare that with reanalysis. In CSM2, it's way too weak. I'd be happy to share that with you. Yeah.
Yeah, we can talk
Okay.
in the break. That'd be good. All right. Thanks a lot. We'll move on to the final speaker before the break. I think, yeah. Asaya Badarunisa Saunidin on looking at moisture sources and pathways for South American rainfall in variable resolution CESM. I think you can point it here, and then,
And where is the,
so if you hold that and point it, it'll appear there. It's
oh,
appearing.
I see, okay. Hi. Okay, so I'm here to introduce to a new set of simulations, new set of interesting simulations that we can use to study the moisture sources and pathways, especially for the tropical South American rainfall, and to study its variability. Okay, so tropical South America is one of those regions where we don't have enough data or literature to characterize the trends in the extreme rainfall events. So all the gray hexagons that we see here, or the tropical South American region, means we don't have enough data. So we are trying to do like a comprehensive study to get a detailed understanding about South American hydroclimate. For that, we are using a high-resolution climate model simulation. And this is part of a bigger project where we also use lake sediment records from tropical lakes, even lakes from remote islands within the Eastern Pacific. So more about our high-resolution simulations. We are running different experiments, but I'm going to talk more about the historic, like preliminary results from my historic simulations. So when I was writing the abstract, I was more ambitious, but right now I only have 23.5 years of historic simulation, so it's going to be like very preliminary output from the historic simulations that I have. And technically, this is not a high-resolution simulation. This is a variable resolution simulation with a nominal 1-degree grid over the entire globe with high-resolution nesting over our region of interest. And when it comes to broader South America, we have 0.25 degree resolution. And by improving the horizontal resolution, we are actually able to capture some of the finer precipitation, details or precipitation structures, which is actually very important for us. Especially, we are going to use this information to like compare with proxy records, which is coming from local, like a specific grid point where the proxies represent localized climate variability. Moving on. So more about moisture tracking. So the moisture tracking in CSM GeoTrace, or the model that we're running, we can actually define the source regions. And from these different source regions, the possible source regions, we can track the moisture until it rains or snows into some region. And this enables us to answer a lot of questions. I'm sorry, okay, I'm just figuring this out. So this enables us to answer a lot of questions, but in the interest of time, I'm just going to show a few tracked moisture from like some of the important source boxes. So we have 17 source boxes from which we are tracking moisture, and then one all land box and one all ocean box. So these 4 are the most, like the oceanic source boxes from which we get a lot of rainfall to the tropical South American region or the monsoon region. And it's not surprising, all of them are Atlantic source region, and during the monsoon season, we get strong wind coming from the Atlantic into the tropical South America. And there are some source boxes in Pacific from which we get moisture coming into the South American region, especially the regions which is to the west of Andes. But regions that is to the east of Andes, it's mostly the moisture is coming from Atlantic source boxes. And the one source region that I want to focus on for this talk is the northern South American land box. So that is the contribution of local recycled moisture or the evapotranspiration which is happening over the land. So the values that we see here is the contribution to the total rainfall. So we see that this northern South American land, or the Amazon box, this green box here, actually contributes about 10 to 40% to the total rainfall, which agrees with all the previous studies. And then this 10 to 40% value, this value differs between seasons, and also it shows a large internal variability. And it changes with modes of variability, so I wanted to see how modes of variability like ENSO or Atlantic Nino, so these are the two modes that actually drives the internal climate variability over the tropical South American region. So during a typical El Nino event, what happens is there is this enhanced convection over tropical Pacific. So we know that it results in a subsidence over the Amazon region, and it results in reduced rainfall over Amazon, or we see Amazon drying. So do we see that in our simulations? Yes, we do see. So when precipitation is regressed onto the Nino 3.4 index, we see this negative precip anomalies over Amazon, but we wanted to see if this teleconnection, do we see this negative anomalies in precipitation which is tracked only from the Amazon box or the tropical South American region, the role of the local evapotranspiration or moisture recycling. So I did a El Nino composite and a La Nina composite, and during the El Nino season we see negative anomalies, means there is less contribution from evapotranspiration or local moisture source, and during La Nina there is enhanced moisture source coming from the Amazon box. And going to Atlantic Nino, so Atlantic Nino is similar to ENSO, zonal fluctuation in sea surface anomalies over the tropical Atlantic. And during the positive phase of Atlantic Nino, we get the eastern Brazil gets positive precipitation, or a lot of flood events over the eastern Brazil, and Atlantic Nino activity is actually maximum during the austral winter season, which is JJA season. So during JJA season, this positive anomalies actually extends even further to the west. Do we see that in our model? Yes, we do. We get this positive anomalies over the eastern Brazil, and then what about the precipitation which is tracked only from the Amazon source box? So we do see a reduced negative anomalies, positive anomalies, increase in contribution from Amazon source box to this region during the positive phase of during Atlantic Nino, and during Atlantic Nina there is a reduced contribution from the Amazon source box to the precipitation over eastern Brazil. So either this is local recycling of the moisture responding to the ENSO, or maybe it's actually reinforcing the ENSO teleconnection over these regions. So yeah, these are the key takeaways. Our moisture tagging and does enhance our understanding of the sources and pathways shaping the region's hydroclimate. And actually, these findings does highlight the complexity of regional precipitation responses and the need to isolate the role of climate change from internal climate variability mods, maybe like using large ensemble simulations in future. Thank you. And I want to give a huge shout out to Ellen Rhodes for developing the grids, and Adam and Jesse for developing this GeoTrace branch of CSM2, and Sophia for all your help, and our collaborators and all the funding agencies and people who work in these funding agencies. Thank you.
Thank you. Any questions? I mean, you're using regional refinement, so it seems like a nice opportunity to look at the impacts of resolution. Have you considered running a low-res version for comparison?
We did run a NE30 PG3 simulation, test simulation, but I didn't do a comparison, but I did a comparison for nominal CSM1. And we are able to capture more finer details, especially in the standard deviation of basin. Yeah.
Any other questions? All right, if not, I want to thank all the speakers again, especially for keeping to time. And we'll reconvene after the coffee break.
And welcome everybody come back to the second session of the CVCWG summer working group summer meeting. And we will start. And first of all, when the speaker comes here, when you speak, you just close to the mic so the online people can hear more clearly. And also for this remote, the top button that's for the laser pointer, the second button, the big one, is forward, and the small one is backward. Okay, now we start. The first speaker is Wei Liu.
Thanks, Aishu. Hello, everyone. My name is Wei Liu from UC Riverside. So today I'm going to talk about simulated Antarctic sea ice expansion, reconciles climate model with observation. Okay, so the motivation of this study. The left panel shows the observed Antarctic sea ice area from satellite, basically the black curve, since 1979 to recent years. So you will see a very robust sea ice expansion before 2015, and afterwards we have a sea ice decline. On the other hand, if we look at climate models, we will see most models will simulate a sea ice decline through the whole period. So here I'm showing the CSM M2 large ensemble simulation, shading for the intermember spread, and the blue curve shows the member average. So you will see a very robust Antarctic sea ice decline. And this is not alone, and this sea ice decline can be seen in most CME5 and CME6 models. On the other hand, if we look at the sea surface temperature change, and the previous study showed that the top panel is observation, we will see over the Southern Ocean from 79 to recent years, we will see a very robust, weak, but robust Southern Ocean sea surface cooling. If we look at the multimodal mean, and we will see instead of cooling, the Southern Ocean show a warming trend. Now we can see the issue, and either in Antarctic sea ice and also in the Southern Ocean sea surface temperature trend. So the model show a decline of Antarctic sea ice, but the observation is expansion. And on the other hand, for the model show the warming, but observation show the cooling. Now my question is that, are they related? Okay, so here is my scientific question. First, will a simulated Antarctic sea ice expansion render the Southern Ocean surface cool, or the other way around, given the ice-ocean coupling? Or to what extent can the bias of Antarctic sea ice change account for the bias of Southern Ocean SST change during the 3 to 4 decades since satellite era? And the last question, how will the Antarctic sea ice expansion associate with other components of the Earth system? So I use 2 papers to answer these scientific questions. All right, so first, let's look at the model simulation. And as I mentioned before, most CME5 and CME6 models simulate Antarctic sea ice decline since 1979. However, I still can find there are several models with some ensemble members that can simulate Antarctic sea ice expansion consistent with observation. So I list all these models on the right in the table, and also with the ensemble members showing the sea ice expansion, and also the other members showing significant sea ice decline. Panel A shows this result, and the black curve shows observation. And on the other hand, we can see the red curve shows the expansion group, and the purple curve shows the decline group ensemble mean, with shading for the intermember spread. Then panel B shows observed sea surface pattern for the sea ice concentration change for observation, C for the expansion group, and D for the decline group. So we can see the historical ensemble simulations from several climate models show the sea ice natural variability enables the models to simulate Antarctic sea ice expansion during 1979 to 2014 under anthropogenic forcing. And this highlights that if we only see the variability mechanism, yes, it could be possible that this natural variability of Antarctic sea ice on decadal time scale can simulate the expanded Antarctic sea ice during this period. So this is very different from previous mechanism because we don't need any interference between the ocean, sea ice, and also atmosphere. Then let's look at the Southern Ocean sea surface temperature change. Again, the panel A shows observation from 1979 to 2014, and the B is expansion group, C is decline group, and D is the difference between the two, decline minus expansion. So we can see, yes, if we can have an Antarctic sea ice expansion, it can allow us to see a cooling change over the Southern Ocean, but only to the north, to the south of 50 degrees. To the north of this latitude, roughly, and we cannot see the cooling change that is different from observation. So I infer that this could be related to the tropical variability. On the other hand, if we look at the difference, and we can see overall, it gives us a bipolar pattern, and we can see the cooling over broad southern hemisphere, especially if we look at the tropical Pacific, we can see the connection between the Southern Ocean and the tropical region in the Pacific. That has been well discussed in many previous studies, show the tight connection. And also, this is not alone. If we look at the Atlantic, we can also see the linkage between the Southern Ocean and the near tropical regions. We can also see this Antarctic sea ice, if well simulated the expansion, it can also influence the ocean heat uptake and also subsurface temperature. Panel A shows observation, temperature change do not mean. If you look at the high latitude, we can see a cooling change in the upper 100 meters. Similarly, we can see the pattern in the expansion group. However, if you look at the decline group, and we will not see the cooling change in the upper 100 meters close to Antarctic, instead a warming change. So if we look at the difference, we will see very robust. This Antarctic sea ice expansion can give us this very robust cooling change. So this is because the net downward sea ice transport that can allow fresh water to be extracted near the Antarctic and released into the open ocean, which will influence the stratification and also the cooling in the surface open ocean water. Reduce the vertical mixing to warm the water beneath, so that is the mechanism for the sea ice influence the ocean subsurface temperature. So one may wondering, and I just grouped the model members that can simulate the Antarctic sea ice expansion or decline. However, there are many other processes going on, so people may be wondering, how can you infer this difference is mainly due to the Antarctic sea ice? So to prove that, and I conducted a sensitivity experiment. So I use CESM1 chemical physics, and I gradually increased the snow and ice emissivity over the Antarctic sea ice area. So it's a time-involving factor. I give this number. I keep it linear because I don't want to add some nonlinear thing. So you will see this experiment is under the historical and RCP scenario. So for the original historical and RCP simulation for the CSM1, which is shown in the blue, we will see still a very robust decline of Antarctic sea ice from 79 to 2013, which is different from observation in black. However, if I just modify this emissivity and I can allow the model to simulate an increasing change over Antarctic sea ice, which is shown in the red curve. So this modification can be viewed as an ice forcing. It's adjust the model to reflect the correct response of Antarctic sea ice to external forcing. So the spatial pattern is shown in the bottom, and for the observation in B and the expansion group in C and D for the decline group. So that allows us to look at the influence of Antarctic sea ice from this scenario. And also, we can look further for the Southern Ocean surface temperature and salinity. So this is my result, and observation for the sea surface temperature change in E and H for the sea surface salinity. So we will see, if we compare with observation, if we have the Antarctic sea ice expansion, we can observe a very robust cooling change around Antarctic to the south of 60 degrees, and to the north, that is a warming change. So for the decline group, similarly, from the previous slides, and it's very robust warming change through all the Southern Ocean. On the other hand, if you look at the surface salinity, we will see the observation give us a increased change for the sea surface salinity close to Antarctic, but outside would be the freshening change. This feature is well captured by the expansion group. However, the decline group gives us opposite change. So that is because the Antarctic sea ice expansion in the expansion group can bring a very robust increasing change to this region, because sea ice forms around the Antarctic coast move northward due to meridional wind drift and melts in the open ocean, so in lower latitudes. So that's why we can see the sea ice increasing change around Antarctic, but decreasing change over the lower latitudes. Okay, so here is my conclusion. First, I found that historical ensemble simulation with multiple climate models give us the result. Sea ice natural variability can allow models to simulate Antarctic sea ice expansion from 79 to 14 under the anthropogenic forcings. Along with sea ice expansion, Southern Ocean surface and subsurface temperatures can cool up to 50 degrees north, and that is consistent with observation. In the other hand, and I skipped the mechanism, but I have this in the backup slide, neither the Southern Ocean Southern Annual Mode nor the IPO, Interdecadal Pacific Oscillation, can fully explain the simulated Antarctic sea ice expansion. However, if we look at the expansion, it's closely related to the surface meridional winds associated with the zonal wave 3 pattern. And further, Antarctic sea ice perturbation experiments demonstrate that the linkage between the Antarctic sea ice expansion and the high latitude Southern Ocean surface cooling and stratification. So that's all I have. Thank you very much.
Thank you. We have to move on.
Oh, wrong time.
Yeah.
Thanks.
Next presentation will be given by Yue Dong on Southern Ocean and ITCZ.
Okay, good morning, everyone. I'm Yue Dong from UCLA. Following the previous talk by Wei, this is another talk looking at broader impact of the Southern Ocean. And we specifically focused on the strength of the Southern Ocean teleconnection and trying to ask how much tropical response we should expect from the Southern Ocean teleconnection. And in the end of the talk, I hope to deliver that the currently simulated Southern Ocean teleconnection strength is likely underestimated due to models' mean state biases. Yeah, so similar to the previous talk, I'm also motivated by this observed SSD trend over recent decades, where we see this pronounced cooling over the tropical Eastern Pacific and Southern Ocean. Also, over the past long-term record, we see this co-variability between these two regions. suggesting the close connection between these two regions. Also, in idealized modeling studies, we often see if you perturb the Southern Ocean in slab ocean model, fully coupled models, we often see a remote tropical or subtropical SST response featuring this La Nina-like SST pattern. So far, the proposed mechanisms involve first the mean state wind advection in the tropical Eastern Pacific, and further, this SST can be amplified by west feedback, the wind evaporation SST feedback, and also subtropical cloud feedback. Especially the subtropical cloud feedback has been identified in this nice paper as a key driver of the intermodal spread in Southern Ocean teleconnections. But then, well, based on this mechanism, we also find that surface winds, especially mean state winds tied to tropical mean state circulation, and probably also precipitation, are also key to the teleconnection. So our guiding question is really, what's the role of the tropical mean state climate, especially the location of ITCZ in the Southern Ocean tropical teleconnections? Specifically, we asked if in one single model, if we were to correct the double ITCZ bias, can we see changes in the simulated tropical response to Southern Ocean cooling? And if so, does it hold for multiple models, eventually explaining the intermodal spread? And if yes and yes, we find a robust ITCZ modulation of this teleconnection, and we ask, does it come about through changing cloud feedback or through other process? So in this work, I'm gonna show a set of idealized CES1 simulations we run, and also a two existing model intermodal comparison project allow us to assess intermodal spread. So part one, CES1 simulations. I use this slab ocean version of CES1 CAMP4 model, my favorite model, which you can see later why. So with fixed radiative forcing, fixed Q-flux climatology, we can run this long-term control simulation to get a mean state. And then on top of that, I impose this regional Q-flux anomaly in the Southeast Pacific to force the Southern Ocean to cool. So you can see some weak tropical La Nina-like ST response, all consistent with previous studies. But in this model, it also has a pretty typical intrinsic model mean state biases, including double ITCZ, the tropical zonal mean precipitation too symmetric between the two hemispheres, and also too weak cloud feedbacks compared to models like satellite observations. So what I'm gonna do use this model is to, in addition to this base set of simulations involving a control run, involving a Southern Ocean cooling experiment, I'm gonna provide two additional sets of simulations, also involving a control and experiment. Except in the control level, I'm gonna do some modifications to address each of these ITCZ or cloud feedback biases, so we can assess how this process change or influence the Southern Ocean teleconnection response. Okay, the first set of a simulation, let's call it flux adjusted or flux adjustment, because I use a modified Q-flux climatology to force the global SST mean state to match observation. And as a result, we see the tropical mean state precipitation looks much better compared to observation, show this asymmetric pattern. And I should also mention that in this set of a simulation, cloud feedback, especially subtropical cloud feedback, doesn't change because we didn't specifically change model physics. So it's just the boundary conditions. And another set of a simulation in the control level, we explicitly change model physics in the radiation code by artificially increase low cloud cover sensitivity to local SST anomalies to match satellite observations. So in this set of simulations, we have stronger cloud feedback, especially over the subtropical Eastern Pacific stratocumulus stack. And this change doesn't actually result in any substantial, you don't see the color because we don't actually see substantial changes in the long-term mean state of precipitation SST. So in this set of simulations, we got a better cloud feedback, but still double ITCZ bias. So now we have three different control runs, which feature different biases, and we're gonna apply the same amount of a Q-flux forcing to see how tropical SST response varies. And turns out in this tropical La Nina-like SST response got amplified in both of these modified experiments, especially in the middle column where it would change the ITC or change the mean state SST distribution, precipitation distribution without changing cloud feedback, but still that leads to a strong tropical SST response. So where does it come from? Is it through the cloud feedback or a different process? So we perform this surface energy budget analysis and then find for left column, for the flux adjusted run, the right column, the cloud-adjusted rounds compared to the base to understand what causes this additional tropical cooling in the top. And we found for cloud adjustment, probably as we expected, the additional cooling primarily coming from the middle right second panel, coming from the shortwave cloud radial flux, which is as expected because we explicitly changed the cloud feedbacks. But for the left column, for the flux adjusted round, we found additional cooling actually more from, or broadly coming from latent heat effect due to wind changes, suggesting stronger west feedback in the subtropical trade wind regions and along the equator, because now we have a better ITCZ, we have stronger southeasterlies, the trade wind regions, and also across equatorial surface southerlies, which enhance this mean wind advections. So part one, in the CES1 simulations, we separate the different process, and we find, yes, indeed, changing mean or improving the mean state does lead to strengthened tropical response to Southern Ocean forcing, and that's mostly through the west feedback, not through the cloud feedback. So next, we're gonna ask, does this process hold in other models and a multi-model project? So we looked at this nice community effort called ETMAP, in which the fully coupled models are forced by this zonal band of heat fluxes, and all of the models tend to show first Southern Ocean cooling because it's directly forced by radial forcing, and also tropical response. And in a previous study, they find the different varying degree of a tropical response is correlated with models subtropical cloud feedback. But here we want to test, does it even related to the tropical ITCZ? So you can see here the zonal mean precipitation, all the models share this double ITCZ bias, but also large spread. So let's define this asymmetric index and then plot it against model simulated tropical Eastern Pacific cooling average over the white box. Now you can see in general models have more asymmetric precipitation mean state, which means smaller double ITCZ bias, also tend to simulate more stronger tropical East Pacific cooling response, which you can also see these regression maps showing that better ITCZ mean state indicates stronger tropical ST response to Southern Ocean forcing. And this is because these better mean states are associated with stronger southeasterlies in the top right, and also cross-equatorial southerlies, which promotes, like we show in the slab rounds, promotes stronger west feedback and the mean wind advection, which contribute to this tropical cooling response. So when I say this strong correlation, I found it very interesting because we know in the previous study, came out of 2022, the tropical ST response in the middle is correlated with models cloud feedback. And this time, we find the same tropical ST response is also correlated with ITCZ bias. So we asked, are these two quantities or even correlated? So we just happen to capture the physics instead of some meaningful physical statistics instead of a physical mechanism. But turns out the answer is no. The correlations between the precipitation index we define to quantify the ITCZ and the cloud feedback metrics are not strongly correlated. It's pretty weak, it's insignificant, and it holds for this subset of ETMAP rounds and also the broader CMAP6 ensemble, suggesting that the intermodal spread in ITCZ and the intermodal spread in subtropical cloud feedback, they don't really explain each other, or at least a large portion. So their influence on the tropical SST response may also operate separately through cloud feedback versus a west feedback process. So the last application is that, what causes the Southern Ocean cooling in the first place still remains a debate. But one of the hypotheses, in addition to natural variability from previous talk, that the Antarctica ice sheets melting. So this is another nice recent community effort called SOFIA, where several fully coupled models all include or add this additional freshwater anomaly around Antarctica to simulate Southern Ocean and global climate change. On the right, you see the multi-model mean. They all simulate Southern Ocean cooling and some degrees of a tropical response. And we apply the same analysis and find, again, models with more asymmetric precipitation and smaller WITCZ bias in the mean states tend to simulate stronger tropical response per degree of a Southern Ocean cooling through the same mechanism because stronger mean state winds. So from here, we can probably infer that since all models share this kind of a systematic double ITCZ bias, then the realistic Southern Ocean teleconnection to the tropics in nature could have been stronger than we currently simulated. Before I conclude, it's just last slide, I promise. This is Southern Ocean pacemaker simulations in two versions of CESM1. Where the Southern Ocean SST anomalies are nudged to observations, we see the remote response. And this paper by Sarah Kent et al. 2023, they find the CESM2 tends to simulate stronger subtropical or remote response, potentially due to this model has stronger cloud feedback. I just wanted to quickly show that actually CESM2 is also one of the models that has much better ITCZ mean state and stronger trade winds in the tropical Eastern Pacific region, which according to our slab ocean runs, according to the intermodal regressions, can also contribute to this subtropical Eastern Pacific ST cooling response. So this summary of the talk, I think basically the key message to the polar community is that to more realistically assess the global impacts of polar climate change signals, we actually need a better tropical mean state to be able to simulate this teleconnection. Well, for the tropical communities, we actually need first the Southern Ocean signals, and then the better tropical mean state to better represent the recent SST trends in the tropics. Thanks, and then I don't know if we had time to take questions.
Okay, thank you. We have to move on. We run out of time. Yeah, we have to move on. Yeah. Okay, next speaker is Glenn Liu. He's talking about the sea surface salinity and the North Atlantic climate.
Hi everyone, thanks for the chance to speak today. So I'm going to present some recent work I've been doing with my advisor Young-Oh Kwon and collaborator Claude Franquinol. So this work concerns the question of what is the importance of ocean dynamics for North Atlantic climate variability, particularly on low frequency timescales. And oftentimes such studies focus on SST variability, but what can we learn by looking at salinity instead? So say you have a temperature anomaly. That anomaly is damped to the atmosphere via air-sea heat fluxes. But for a salinity anomaly, you don't have the same atmospheric damping. However, both variables are impacted, presumably by the same ocean processes, like diffusion and mixing, horizontal advection, and vertical processes like entrainment. So you can often think of salinity variability, particularly the damping of salinity, as sort of the representation of the sum of all these ocean processes. But considering all these different processes, how do these different processes individually impact salinity variability? And what can we then, in turn, can that tell us anything about the role of these ocean processes for North Atlantic climate? So for this study, I really focus in on the sort of vertical entrainment, local vertical entrainment, and try to investigate that using a simple model. You might be familiar with the Franquinol and Hasselman stochastic model. So the idea here is that temperature changes are driven by atmospheric forcing, which acts on much faster time scales. So you can think of it as white noise of a certain amplitude. And you also have damping to the atmosphere, whose strength is determined by a linear coefficient, lambda A. All of these parameters, however, do vary seasonally. And when you think about the winter, you have much deeper winter mixed layer depths in the ectotropics. In the summer, the shallow thermocline insulates anomalies from the previous winter of interaction from the atmosphere. And the following fall, as the mixed layer deepens again, these anomalies are entrained back into the surface, leading to winter recurrence, known as the reemergence mechanism. So you can represent that in the stochastic model of the addition of an entrainment term. And what I'm showing here is the persistence or autocorrelation function of SST anomalies. And you might notice that the white line, which is CSM1 with full ocean physics, is represented pretty well by a simple stochastic model of 3 terms in orange, suggesting that it's a pretty good representation for SST just considering these processes. But the question is, does this also apply for salinity as well? So for salinity, we can use stochastic evaporation and precipitation forcing. Again, there's no heat flux damping, but we have the same entrainment mechanism. Furthermore, these anomalies beneath the thermocline might be damped by subsurface processes, so we can include a simple damping term to represent that subsurface damping. So I won't go into the details of the parameterization in the interest of time, but essentially we estimate these parameters based on CSM1 large ensemble, the historical period, and see if the simple model can replicate salinity behavior in the full physics ocean model. So to start off, let's think about kind of the autocorrelation function again, and a kind of simple quantification of the strength of reemergence. You can just difference the winter maximum with the summer minimum to get sort of an index of reemergence. How does this look like in CSM1? We have the pattern here, strong reemergence where you have deep wintertime mixed layer depths, no surprise, and some kind of larger values in the subtropics. So does the stochastic model reproduce this? And we integrate the stochastic model for 10,000 years at each point. We do this calculation, and you can see it does a pretty good job. So again, there's no horizontal circulation in this simple model, but it seems to be capturing many of the features of seasonal differences in persistence. Let's kind of zoom in on a point with pretty strong salinity reemergence to understand what's happening. So again, I'm showing the wintertime autocorrelation for CSM1. This is the target. We have the stochastic model with just entrainment, no subsurface damping, and see that that's not enough. Sea surface salinity is too persistent. But when we add in subsurface damping, that substantially improves the representation of salinity persistence, but it's still too persistent on longer timescales. And I just wanted to bring in SST. As I mentioned earlier, the stochastic model does a much better job with SST, and, but you can see the importance of subsurface damping really comes in for salinity. So we've been talking about persistence. But what about variability and the amplitude of variability and its patterns? So I can take the average of SST over the basin, apply a 10-year low-pass filter, and regress that back to the SST anomalies to get the pattern of variability for CSM on top and stochastic model on bottom for SST. The takeaway here is that the pattern is pretty similar, but the stochastic model is underestimating the level of variance at low frequencies. And we have the opposite problem for salinity. In this case, salinity is too energetic in the stochastic model in the absence of horizontal dynamics. You can see here that the variance has about 1.6 times the level of variance in CSM1. So the kind of takeaway here is the missing dynamics from the stochastic model beyond entrainment, such as horizontal circulation, seem to have different impacts on SST and SSS. So that brings me to the main takeaways. We see that a simple model with no horizontal circulation does a pretty good job of capturing the pattern of seasonal differences in reemergence in a model of full ocean physics. We also see that subsurface damping is pretty important for capturing the level of long-term persistence in salinity. And finally, kind of the main takeaway here is like, what have we learned about North Atlantic climate? We learned that these sort of horizontal ocean processes impact temperature and salinity differently. So you can't necessarily generalize an impact on salinity and use that to apply that to SST. So yeah, that brings me to the end of the talk, and just wanted to thank the organizers for travel funding to attend this event, and yeah, happy to take any questions.
Any question?
Thanks, Glenn. That's really neat work. I was wondering if you'd explored the use of a linear inverse model as a multivariate stochastic integrator and something to take into account non-local effects.
Yeah, I have not explored that, but it'd be really interesting because this is a fully local model, so yeah, we don't consider any of the non-local effects, but it would be really fun. We could talk more about implementing that, but I'd be really interested.
Any other question? Oh, I have a quick question.
Oh, sure.
Possible you make the green curve is more close to the white one? Like now you said you added a subsurface damping term, and
yeah.
What else you can do to make it the salinity perform better?
Yeah, that's a good question. I guess one thought is maybe some sort of way to add horizontal advection into the model. So maybe that could provide an additional source of damping to salinity, but still thinking of how to do that in a fully local model. So maybe some way to kind of parameterize the effect of horizontal advection. But yeah, that's a good question, and still need to think a little bit more about how to increase complexity to reach that level.
Any other question? No? Okay, let's move on to the next talk. Thank you. Next talk will be given by Kai Huang. It's written on the QBO and the MGO.
Okay, cool. So good morning. I'm going to present our recent work on the QB-MGO connection. And this work was done in collaboration with local NCAR scientists as listed here. So yeah, I will begin with some brief introduction of the QB-MGO connection. So the QBO was found to have very significant impacts on the MGO, like it was found nearly 10 years ago. Like if you look at the MGO propagation amplitude, and if you define the QBO at 50 hectopascal level, you will find MGO tend to be stronger and more likely more likely to propagate across the maritime continent in the QBO easterly season than the QBO westerly season. And if you track all the MGO events in the NDGFM season from 1979 to 2020, and you will track all 81 MGO events, and you subset them into the QBO easterly phase and QBO westerly phase, and then do a difference for the Hofmuller diagrams in the precipitation anomalies, you'll find much differences over the Western Pacific and maritime continent region. That is inconsistent with our findings here, like MGO is stronger and more likely to propagate across the maritime continent. And there are several unique aspects of this QB-MGO connection. First, is seasonality. This QB-MGO connection is only seen in the winter seasons. And second, the location preference. Like the QBO's influences on MGO is centered around the maritime continent region. And then the uniqueness, like among all the other convectively coupled equatorial waves, MGO is the only one to feel the impacts from the QBO. And then the last, its emergence, like you can only detect the QB-MGO connection in the reanalysis datasets after the 1980s, but before the 1980s, you don't see such strong connection in the reanalysis datasets. And in the past decade, several mechanisms are proposed trying to explain the QB-MGO connection as listed here, but I will still say the connection is not thoroughly understood. Other than that, all climate models suffer from the missing of this QB-MGO connection, and even with a prescribed stratosphere through the nudging, so the QBO signal is the same as the observations, still the QB-MGO connection is missing there. And last, the QB-MGO connection is somehow magically slightly captured by the forecast system and some of the MGO case simulations as listed here. So it turns out, like if you look deeper into the QBO's modulation on the MGO, you will find QBO not only modulates the MGO propagation and amplitude, it also modulates the environmental conditions for the MGO convection to happen. So here, this diagram actually are showing you the environmental moist static energy anomalies for the MGO precipitation anomalies in the x-axis, and also at different days of the MGO as listed by the y-axis, and day 0 is when the MGO convection is over the Indian Ocean region. And so if you look at the shading, colorful shading here, it actually tells you at a specified MGO precipitation anomaly and at a certain day of the MGO life cycle, what will be the environmental MSE anomaly be like. And you can do that composite for the 28 MGO events that in the QB easterly phase and 34 MGO events in the QB westerly phase. And you do a difference between these two diagrams in the QB easterly minus QB westerly, you will find some interesting features here. So first, after day 0, you'll find the positive MGO precipitation anomalies, the environmental MSE actually get increased in the QBO easterly phase, and vice versa for the negative MGO precipitation anomalies. That is to say, like when the MGO convection happens in the QBO easterly phase, even with the same precipitation anomaly intensity, the environmental MSE is actually higher, provides more energy for the MGO convection to consume. And the MGO is therefore become more mature and more efficient in removing that MSE anomaly, like in the QBO easterly phase than in the QBO westerly phase. And if you are familiar with MGO dynamics, this is actually a very favorable condition for the MGO to develop. And other than that, before day 0, from day roughly -5 to -15, you will see a very interesting precursor of higher MSE, even for the negative MGO precipitation anomalies before day 0. So remember, like the MGO convection is a dipole mode. like to the east of the MGO active convection, it is a suppressed convection phase, and at front of the MGO active convection. If you somehow get higher MSE to the front of the MGO active convection, then in the following days, when the MGO active convection moves there, it is obviously get stronger and more mature. The question is, like, what is really going on here in these preceding days of the MGO active convection? To investigate that, we did another composite analysis, but for the moisture anomaly and dry static energy anomaly vertical profiles, also binned by different MGO precipitation anomaly values for day -15 to -5, where this producing, higher MSE anomalies happens. And if you do the differences between the QPO easterly and QPO westerly phase, you'll find like for the mild to negative precipitation anomalies of the MGO convective system, in the middle to lower troposphere, you will see a very overall wetting and a warming signal here. It seems like some convective processes are happening here in the QPO easterly phase. And then we also checked the vertical profiles of the MGO vertical velocity, but we do not see the corresponding changes in that. That is to say, like this wetting and warming producing, signal to prepare the MGO convection to better develop in the QPO easterly years are not coming from the MGO system itself. So where does it come from? It turns out it is coming from these changes in the MCS or mesoscale convective systems. So here the maps are the composite maps for the MGO precipitation with bandpass filtered precipitation anomaly, which are represented by the contour lines here. And the MCS precipitation are represented by the shading colors here. Yeah. So we did the composite for the QPO east phase and west phase, also based on the RMM index for the MGO. So the top two panels are actually showing you the days, a composite for the days where the MGO are inactive. That is when the RMM index amplitude are below 1.0. So in the QPO east years, if you look at the shadings here, you'll find much increased MCS activities or precipitations west of the maritime continent. While to the east of the maritime continent region here, the MCS precipitations are suppressed here, and vice versa in the QPO west phase. Like to the west of the maritime continent region, you get decrease in the MCS precipitation, but to the east of the maritime continent region, you get an increase. So I won't go into the details why this happened, but this is relevant to QPO's ability to modulate the MCS propagating, behaviors. Like it is more westward propagating in the QPO east years and more eastward propagating in the QPO west years. Other than that, we can also do the same composite analysis for these two variables, but based on the RMM phase when the MGO are in the active phase, that is when the RMM amplitude are greater than 1.0. And these maps are showing for the MGO days in the QPO east phase. Like in phase 1, the MGO convection is mostly here, and MGO suppressed convection is west of the maritime continent region. But in phase 1, you already see some scattered, MGO convection. In phase 1, in the MGO suppressed convection, you already see some NCS activities here. And in the next phase, phase 2, it gets collected by the MGO convection envelope and become part of the MGO convection. And at the same time, the new MCS activities are identified again to the east of MGO convection. And in phase 3, it is absorbed by the MGO convection envelope and become part of the MGO convection. And what's more interesting is when the MGO is about to cross the maritime continent from phase 4 to phase 5. Like, look at here in phase 4, the MGO convection is mostly over the Indian Ocean and the western maritime continent west of the 120 degree east. But east of the 120 degree east, in the suppressed phase of the MGO convection, you get very strong activities in the MCS precipitation, and which you will not see if you look at the climatology. Like here is actually the whole of the MCS activities. But with the help of the MCS convective, precipitations, in phase 5, the MGO follow the path of this preceding MCS precipitation and propagate across the maritime continent as a result. So that is for the QPO east phase. How about the QPO west phase? So we did the same composite analysis here. And it is very interesting, like in phase 1, you get a decent amount of the MGO convection here, but in the suppressed phase, you don't get much MCS precipitation over the maritime continent. And as a result, in phase 2, like the MGO convection cannot develop very well. It here, like phase 3, when you see these stronger MCS precipitation anomalies over the Indian Ocean, and then in phase 4, like you get decent amount of the MGO precipitation again. And in phase 4, like when the MGO is about to cross the maritime continent region, compared with what we saw at the QBO easterly phase, where you are seeing this, enormous amount of the MCS precipitation anomalies here, but in the QBO westerly phase, you don't see it here. Like it is very suppressed, and as a result, MGO could not propagate across maritime continent region without these preceding MCS precipitation anomalies. So finally, some take-home messages. First, we found that QBO could modulate MCS propagation over the maritime continent region, leading to more local MCS activities over the Indian Ocean in the QBO easterly season. And this increased MCS activities pump moisture from the boundary layer to the free troposphere, creating a favorable weather and warmer environment for the following development of the MGO convection. And then MGO is therefore become stronger in the QBO easterly phase and more likely to propagate across maritime continents with the guidance of these MCS precipitations. And now I'm trying to use this potential new theory to explain the several unique features about the QB-MGO connection. First is seasonality. This is probably due to the fact that MGO cross the maritime continent through the southern sea surface, where the MCS activities are strong only in the winter seasons. And secondly, the location preference, because that is due to the MC is the area with strongest MCS activities in the tropical Indo-Pacific region, and uniqueness. That is due to the fact like MGO relies more on the moisture variation than other tropical convective systems. And the emergence, like that is probably due to a data quality problem. Like no MCS satellite observations are fed into the real analysis datasets before the 1980s. Maybe the QB-MGO connection is always there, but due to this data quality problem, we cannot detect that in the real analysis datasets. And why this is missing in the in the climate models, that is due to the fact like the MCS simulation remains a problem there, and why this is somehow detected in the real analysis and prediction system, even with the biased MCS simulation there, that is probably due to like the regional wetting and warmer effects of the MCS could be assimilated into the initial field of these systems. So these systems could capture the QB-MGO connection there. And I will stop here and take any questions.
Thanks, Kai. Since we are running out of time, and we don't have the questions for now. If you have any questions for Kai and Wei and Yue, you can ask them offline. Next speaker is Charlotte Dimond. She's talking about the climate sensitivity.
All right, good morning. So this is a talk that is really just asked the question, how does the treatment of some of our parameterized physics in the CESM2 affect its mean state and variability? And I tend to approach this problem really from the perspective of trying to understand how does it affect the Madden-Julian oscillation. But for here, I'm going to try to take sort of a broader scope and just introduce this with a couple of figures from a recent paper by Aaron Donohue, who has shown that for many of CMIP, from CMIP 3 through CMIP 6, most coupled models tend to underestimate ocean heat transports and overestimate atmospheric heat transports. And one of the leading causes for this bias, according to their paper, is that the models are extracting too much energy from the ocean surface in the subtropics through evaporation. So, of course, some of this excessive evaporative heat or evaporative flux from the ocean can arise from things such as too strong winds, too warm SST, perhaps too dry upper marine boundary layer. But the question I'm going to address today is, what if there are biases in the way we're actually computing the flux that could contribute to this? And so we've done some previous work that has shown that when we change the bulk surface flux parameterization in CESM2 to that by developed by Bill Large and others, Large and Pond, that we tend to get an improved simulation of the MJO in atmosphere-only simulations. And so this is the next step to say what happens in the coupled system. And the take-home message is it's very complex, but I'll try to walk you through this. So this is just a quick picture to show global latent heat flux estimates using a variety of reanalysis products. In the top 2 rows, satellite products here, and some other types of products or hybrid products. The algorithms used to compute the fluxes are listed next to the titles. You can see that all of the satellite products use the core flux algorithm developed by Chris Farrell. And so we're going to implement the core flux algorithm into the CESM2. This has been done before, but I want to show you a couple of additions that we've done. One of the motivations for this comes from a paper by Brunke et al. In 2003 that showed that the Core 3.0 algorithm is among the least, or the overall least problematic, that's their phrase, bulk flux algorithm. So despite the biases you may have in your wind speeds, for example, the idea is you should at least be computing the fluxes to the best of your ability. Okay, and so here are what could be improved. Good, you can see this. So the first is the bulk transfer coefficient. So if we swap the Large and Jaeger, the gray curve bulk transfer coefficients with those from the core, you can see that we should overall reduce the evaporation from the global oceans. But the core algorithm has 2 additions that we are also implementing. One is the ocean cool skin effect. Molecular thermal conductivity limits, it actually reduces the few upper millimeters of the ocean surface temperature by about 0.3 Kelvin compared to just below this very thin layer. The second one is the diurnal warm layer effects. Now, Large and Caron actually implemented this in CESM 1, I believe, when the ocean and atmosphere are coupled once per day. But you still need this when you have a 10-meter vertical resolution, as shown here with the blue curve, versus 10-centimeter vertical resolution. This is done with 1D. So you will drastically underestimate the effect of ocean diurnal warm layers without this. Okay, so what we did is we are going to show you some comparisons between the default model, which I've labeled Large and Jaeger in gray, the CESM, or the core bulk flux algorithm with just the exchange coefficients, and then what I'm calling the core 3.6 plus, which includes the cool skin and diurnal warm layer effects. So just to get started, when we implement just the core bulk coefficients in the CESM2, this is fully coupled. These simulations were all run for about 35 years. We can see that, somewhat contrary to what I expected, we see a reduction in global sea surface temperatures. But when we add on the cool skin and diurnal warm layer effects, this is offset somewhat. And so the total effect is shown here. And if you're familiar with CESM2 SST biases, you can see that this effect would offset some of the biases in that model. When we look at rainfall, the main take-home message is that we seem to see an enhancement of the Hadley circulation. So we have more rainfall in the tropics along the equator, slight reductions in the subtropics. And in the interest of time, I'm going to go straight to the MJO. So what we're looking at is these are Hav-Muller diagrams of MJO propagation from the Indian Ocean across the maritime continent, which is shown with the box, into the Western tropical Pacific. And so the numbers that you see here, this is the standard deviation of rainfall at this base point. This is slightly underestimated in the default surface flux parameterization. When we go to just the bulk transfer coefficients, you can see that the coherence of the MJO is degraded. although the amplitude of the MJO in the Indian Ocean increases. When we include the cool skin and the diurnal warm layer effects, we see a recovery. We see a reduction in the variance, but it's still greater than what you saw in the default. And we have largely restored the eastward propagation of the MJO. And within this box, you can see that we have better coherence across the maritime continent. When we look at ENSO, what I'm showing here, this is the autocorrelation. This is from the ERSST from this period, which is the closest available match to the time period of our simulations. The longer term variability is shown on the light gray curve for reference. So just to give very broad sweeping statements about what the biases are in ENSO, for the default case, we can see that ENSO is too periodic and it has weak asymmetry compared to observations. When we move to the core bulk transfer coefficients, this too strong periodicity remains and the weak asymmetry remains as well. It's not until we include the cool skin and diurnal warm layer effects that we see changes that tend to reduce the overly periodic behavior of ENSO, but also improve the asymmetry of the signal. So this is just a quick summary. These are very new results. There are an infinite number of problems we could look to explore. I'm a tropical person, so this is what I've looked at. But the main take-home points is that the bulk transfer coefficients alone can actually have negative impacts on variability compared to the default surface flux configuration in CESM2. It's not until we go to the inclusion of the cool skin and diurnal warm layer approximations that we see the greatest improvements. And then I just want to close with some thinking ahead towards CESM3. When we go to the MOM6 ocean, the near surface vertical resolution will increase from a 10-meter depth in CESM2 to 2.5 meter depth in MOM6. This means that the diurnal warm layers and perhaps rain layers, which I haven't talked about here, can be directly simulated. The cool skin effects must still be parameterized. And then why the core bulk flux algorithm? Again, it's one of the least problematic algorithms when compared to direct covariance flux measurements. It was developed specifically with global marine surface flux measurements collected from various field campaigns. And then getting the flux right seems to improve some aspects of variability with what I feel like are maybe rather minimal changes to the mean state, although more scrutiny of that point is needed. So I will close there.
Because of time, we just move on. Thanks.
All right, thank you.
Okay. Our next speaker is Crazy. And he's
in recent years, I spent a lot of time producing new parameterizations of organized convection for climate models. And this has used a new idea about the coherent structure issue, representing organized convection as coherent structures in turbulent environments. And we've got had a lot of success in terms of GCMs. In fact, for the NCAR model, the DOE model, and the the British UM, we have an increased representation of the Mad-Julian oscillation. So, in fact, that is the major. It's not working. Oh, here we go. In fact, I'm particularly interested in different types of Madden-Julian oscillations. You notice here that this is a Madden-Julian oscillation, and there is definitely signs of what ends up by being tropical cyclones. So that means there's a totally different transport methodology. And so I'm going to compare now the vertical momentum transport by the MJO and the association with these tropical cyclone-like circulations. I'm going to be using super parameterized numerical simulations and the analytic representation of that. It's not working. How do you see? In fact, this is the representation. This is the representation of a change from convectively coupled systems like MCSs to the MJO in a global model with organized convection explicitly simulated. And I'm going to be looking now at the I don't know why this is not working.
Would you like me to advance them for you?
Yes.
I can advance them for you if you like.
Yes, please. Please do. Next one, please. The MJ system occurs after a particular length of about several days, about 40 days in the simulation. And you'll notice that the vertical structure is very interesting. There are strong westerly bursts. The westerly bursts are a very interesting business in terms of the MJO and its effects. Next. And the middle diagram here shows the typical circulation in an MJO. The vertical tilted rearwards and of three types. Next simulation. The interesting point about this is that there is the presence of Rossby gyres in the simulation, just like what there was in the first diagram I showed you. And in fact, these Rossby gyre-like circulations within MJO circulations, I think, is a very important thing. Next picture. So I'm going to compare the vertical momentum flux now due to the vertical convection, the organized convection in the MJO. You notice that the vertical momentum fluxes are negative. That's quite typical in MCSs and in the MJO. And on the left, on the left here, you see the analytic model, and the other side is the numerical simulation by Grabowski. And you notice they agree quite well. And the vertical negative to vertical momentum flux contribution produces westerly wind burst type circulation. Next one, please. This goes over to the Rossby gyre-like circulations within the MJO. And you notice on the right, again here, the numerical simulation and the analytic model. It's very, very similar. In fact, the red region is where you get westerly wind bursts. This one here should have the red circle, the red diagram in the middle. So that means that the generation of momentum flux, and particularly to the westerly wind burst, is a very important part of the whole circulation. So what are the takeaway comments here? I've shown here that the analytic models agree very well with the numerical simulations. And the MCSP, the representation of organized convection, overcomes the gray zone problem of representation of organized convection in GCMs. And this means that that increases, that extends traditional parameterizations. And the convective momentum flux by the MJO and the Rossby gyre-like circulations in the MJO, in fact, in certain circulations, is an important part of the westerly wind burst, and therefore in an El Nino situation as well. And it's also salient to the MJO that Kai was talking about. So there's a new approach, basically, to representing the MJO in climate models that has a definitely effect. And the Rossby gyres, in fact, the contribution by the Rossby gyre-like circulations exceeds that due to the MJOs themselves. In fact, this may actually explain partly why the El Nino situation is very different, has very different distributions of heating, and some of them are stronger than others. I would suggest that it's the horizontal transport due to the gyre-like circulations within the MJO that's causing that change of amplitude. But this is totally a theoretical and numerical result, and I would be interested to know if there's any realism in reality, so to speak. Thank you.
Have a couple of questions. If not, let's move on to the next talk, which will be given by Kwesi Kwagrin. We'll talk about how do atmospheric rivers change under warmer climate versus climate engineering.
Just give me a second to pull up your slides.
Okay. Well, as they pull up my slides, I know a lot of people will be wondering, is this Kwesi? Yeah, this is Kwesi. I'm the other one, so yeah. Just to clear your mind, this is Kwesi Kwagrin. Okay, thanks a lot for pulling up my slides. So today we want to talk about atmospheric rivers in the stratospheric aerosol injection experiment. This is work that contributed to my PhD. So I recently defended, and I passed, yeah. So this is work that has had contributions from my advisor, which I'm very thankful for, Dr. Travis O'Brien, and another Kwesi, and Ben Kravitz, and Simon Towns. So let's talk about atmospheric rivers. So these systems are very large moisture transports that bring a lot of rainfall to the cold polar regions. So what I'm showing here in this movie here is water vapor that is in the atmosphere. This is in the Atlantic. And you can see these orange long lines. So these are what we call atmospheric rivers. So the panels A and B are showing us the plan view and the cross-section view of atmospheric rivers. These have been identified mostly over the West Coast as baroclinic wave propagating rivers in the atmosphere. So they bring a ton of water vapor, and they can cause a lot of precipitation and lead to a lot of dire consequences. So why do we care about these atmospheric rivers? Because one, they bring good amount of precipitation to water-stressed regions and also help in drought relief. However, they can contribute to extreme precipitation globally. Like the literature has shown that atmospheric rivers can cause a lot of flooding event. So this event here, which is Bloomington, Indiana in 2021, was an atmospheric river event that brought about 6 inches of rain in 8 hours. So they can bring a lot of rain, a ton of it. This is also downtown of Bloomington. We had 1 casualty from these extreme precipitation events. So they are very important. They also happen in Santa Barbara, and most of the West Coast. They bring a lot of mudslide and landslide. This event, which is not playing in Santa Barbara, had about 10 foot of landslide. So we had buildings that were tearing apart because of that back-to-back atmospheric river event that was happening there. So they are catastrophic when they do happen at the extreme level, but they are good as well. So we want to see how they will change in the warmer climate, but also look at how they will change under stratospheric aerosol injections. So the problem is that we do not really know how they will change under SAI, but we know that under SAI, there's going to be a reduction in the global mean surface temperature. So that means that we would expect that precipitation will be affected, but we don't know what the sign or the signal for these changing atmospheric rivers will be. So that's what we're going to talk about. So the data we use the SSP 245 scenario, which is more representative of the current pathway I think we are trajecting on, and then also compare that with the SAI 1.5 from the ARISE simulations. So what we do is that we split the duration into the near future and the far future, the mid future, sorry, and then we detect atmospheric rivers using this toolkit for extreme climate analysis, which was developed by my advisor and some colleagues. We then characterize atmospheric rivers based on their impact to see how they will affect precipitation. So now let's look at some results here, just to give us an understanding of what we are looking at. The first row is going to be talking about the near future, the second row is going to be for the mid future, and the last row is going to be for the entire duration, which is from 2035 to 2069. The first column is for the SSP experiment, the second column is for the SAI experiment, and the third column is the difference between the SAI and SSP atmospheric river days. So what we are looking at here is the atmospheric river days per year. So a couple of things to note is that during under the SAI experiment, we have a retreat of atmospheric rivers from inland regions. We can see this in the North American region and also in the Australian coast. So we see that under SAI, we have this reduction in the number of AR days, whereas under SSP, we have some atmospheric rivers penetrating inland. And recently, my lab and I in 2024 did a work on emergence of atmospheric rivers in the Midwest, and we can see that even represented here. So these are not just West Coast phenomena as we initially thought, they happen in the Midwest as well. However, although we have this fewer inland ARs, under SAI we have more oceanic ARs happening, which was quite interesting for us to see. We have these about a magnitude of 15 to 30 more ARs happening per year in the oceans under SAI. So that was a cool result to find. We tried to find out why this happens in our paper that is currently under revision. Also, we look at the latitudinal extent of atmospheric rivers, and we see that under SAI we have more ARs restricted to the mid-latitude as opposed to under SSP. So this means that under SAI we would expect that most ARs will be region-focused, that is more in the mid-latitude. And this is quite interesting. We might think these intervals are small, but 1 degree is to about 100 kilometers. So we are having a change of location by about 5 degrees, that's about 500 kilometers. Putting that in miles, that's about 200 miles change in the location of atmospheric rivers. So the SAI experiment changes what we see in atmospheric rivers quite a lot. So I want to characterize atmospheric rivers based on a scale that is a Ralph et al. Scale, which tells us about the impact. So how long do we have an atmospheric river over a location, and how does it affect precipitation? So we have weak atmospheric rivers, which are about 250 kilogram per meter per second to 500, and we have the exceptional atmospheric rivers, which can bring about 1,250 kilogram per meter per second of moisture to a region. And when they persist for longer times, they can lead to heat waves. We've seen that in the Pacific Northwest, heat waves and all that. So yeah, we would also want to look at moderate and good ARs, which bring not extreme rainfall, but good amount of rainfall to the region. So we'll characterize all that in just a bit. So in this panel, what we are looking at, these two panels, we are looking at the difference in the categories of ARs that happen under SAI relative to ARs that happen under SSP. And what we see is that under SAI, we have more an increase in the beneficial ARs. That is ARs that do not bring a lot of rainfall or are not that catastrophic. But under SSP, we saw that there was going to be an increase, but it's reduced totally under the SAI. And we see this happen in both the northern hemisphere and the southern hemisphere. One thing that we see is that we have more category 3s that are projected under this SAI experiment in the northern hemisphere relative to the southern hemisphere. And then the longitudinal extent also tells us something similar, but just tells us the locations. We see that there's going to be, there's a projected increase in category 3s, especially over the Pacific region. So we are still concerned about why do we care. So we want to look at precipitation because nobody is living in the atmosphere to be affected by ARs, but when they do precipitate, they affect us. So we want to look at how precipitation changes. So what we see is that these figures are similar to what I showed initially. The last column is what we are going to be focusing on. We are going to talk about the changes in precipitation. So under SAI, we have more drier, we have less precipitation compared to the SSP. One thing that I want us to note, which probably affects us, is the West Coast precipitation from ARs. We see that we have a reduction in precipitation under SAI over the West Coast specifically, and also over Southern America, the East Coast of North America and Southern America experiences these reductions. So a few conclusions. We did a couple more to test why we see these changes. It's basically thermodynamics, that the thermodynamics outgrow the dynamics. So that means we have more water vapor in the atmosphere and the SSP. That's why we are having all these changes. So the conclusions we draw from our experiment with this one scenario, I would want to highlight on that because this is just one scenario of SAI experiment, is that SAI has a potential to reduce AR-associated rainfall and also has the possibility to reduce catastrophic atmospheric rivers. That means we'll not be having these extreme category 5s and 6 that are very, very, very destructive. And the last thing is that SAI increases beneficial rainfall. So that means people in the California coast where they need a lot of water and there's a lot of drought, they can benefit from these atmospheric rivers that do happen over there. So thank you. And I would like to thank my collaborators and everybody who played a part in this. Yeah, thanks a lot.
Thank you. We can have one question.
Thank you. Nice talk. So I'm curious, first question, in SAI, are the aerosols homogenously distributed? And second question, if so, in a real-world application, they might be distributed in isolated locations, and what might that effect be?
That's a very good question. So that's something that we are thinking of addressing. I think in the ARISE simulation, they are homogeneously distributed at 30 degrees north, 30 degrees south, and 15 and north. Yeah. So they are homogeneously distributed, but we are trying to see, since this is just one experiment, it's difficult to quantify the differences or the biases based on the locations, but it will be something that will be very interesting to see. I know Christine Schultz has a paper that looked at just the West Coast and looked at the GLANCE SAI experiment, and they show that there are some inhomogeneities even in the location of ARs and all that. So it will be very, very interesting to see, but this is like a very new branch looking at SAIs and ARs and the SAI. So yeah, we'll try to answer that question in the near future, but yeah, thanks a lot. Yeah, thank
you.
Thank you.
Well, the next talk will be given by Harasuki Hirasawa. This talk also on the geoengineering. This is instead of a sulfate injection, this is for cloud brightening.
Okay, yeah, good morning, everyone. So I'm going to be presenting some results from a development of a scenario that we're hoping to include into the GeoMIP intercomparison, focusing on using mid-latitude marine cloud brightening simulations to get something closer to what the SAI community has developed for their scenarios. And so this is work that I've done. So I ran some CESM and E3SM simulations, and then my colleague Matthew at the University of Exeter ran some UK ESM simulations for this work. So yeah, marine cloud brightening, it is one of the main proposals for solar radiation management or solar geoengineering. And so in contrast to SAI, which focuses on stratospheric aerosols, marine cloud brightening aims to leverage the Toomey effect specifically. So it's this idea that if we inject aerosols into the lower marine boundary layer over the oceans, they will interact with the clouds, increasing the number of cloud droplets, and then each of those cloud droplets will, since they're smaller, they'll reflect more incoming sunlight. And so that will, in turn, reduce the shortwave downwelling at the surface and create cooling. So this is then modulated by adjustments in the clouds. So when we were putting together the design for this protocol, we sort of wanted to address three main questions. So first is how we represent the MCB in the GCMs. The second is where MCB should be deployed to get perhaps more ideal or more less harmful climate impacts. And then once we have that information, we can run some of these scenario simulations to determine when and how much MCB is required to cool. So the approach we're taking is to apply increasing sea salt aerosol emissions. This is a figure comparing 6 different atmosphere-only models. And so the solid lines are showing the all-sky forcing, and then the dashed lines are showing the cloud component of that forcing. And so what we find is that, so first off, we specify an increase in accumulation mode sea salt aerosol. This is not as simple, this is not really a simple thing to do. So depending on the model, accumulation mode aerosol means different things. And so actually a lot of the variations we see across the models is the result of different emission rates. So since the mass of aerosol emissions scales as the cube of the dry radius, if you have a larger aerosol emission, the mass emission scales quite quickly. And so, yeah, since we have this large uncertainty in the aerosol radiation from the, in the ERF due to these injected sea salt aerosols. So in our case, we're looking at a range from, for example, at 50 teragrams per year, from -7 watts per meter squared in NOR-ESM and all the way down to essentially a negligible forcing in the GFDL model. So in order to ensure that we're getting similar forcings across the models, we are explicitly defining a fixed SST simulation in order to benchmark the forcing that we get from sea salt aerosol. And the idea is that rather than specifying a set amount of sea salt aerosol emission, we have all the models determine what sea salt aerosol emission gives you a target ERF, in our case, 2 watts per meter squared. And so the other thing is, recent work on MCB simulations has found that when you apply marine cloud brightening in the subtropical Pacific and Atlantic, you end up producing this La Nina-like cooling signal. And in a lot of cases, this is probably undesirable to, for example, in CESM, which is in panel G here, we end up getting some regional warming as a result of MCB. And so when we apply MCB in the subtropics, that might actually exacerbate warming regionally. However, when we shift the emissions towards the mid-latitudes, we find a couple things. So the first is that at least in CSM and E3SM, actually the forcing is more efficient at mid-latitudes because there's more low clouds to brighten. And then we also find that the feedbacks are less negative in the mid-latitudes, and so we get more cooling per unit forcing when we are applying MCB in the mid-latitudes. And then finally, we see that in general the cooling is more uniform, and so we don't get any of those regional warming signals that we got, for example, with the subtropical MCB case. And so so going forward, we decided to focus on this mid-latitude ocean MCB scenario strategy. Since, I figured I'd include this because this is sort of relevant to our, when we're designing the controllers. The algorithm that adjusts how much MCB we're putting into that atmosphere. Actually, when we compare across the models, the subtropical versus the mid-latitude MCB cases, the response timescales are actually quite different. And so in general, the global temperature response tends to saturate much more quickly to a constant sea-salt aerosol forcing in the subtropics rather than in the mid-latitudes. And then we also get fairly substantial differences across the models too. So in the case of UKSM, it takes there's an E-folding time of about 5 years versus almost 15 years for E3SM. Okay, and so the actual protocol that we're using is going to be similar to a proposal for SAI, which is that MCB begins in 2035. And then we target the MCB emissions in order to maintain temperatures at 2020 to 2039 global mean surface temperatures. So this is roughly a 1.5 K target. And so these are the emission rates on the top row, and then the temperature time series on the bottom row for the 3 models that we ran. And so I think one thing to point out here is that if you take a look at the y-axis on the top row, we are using a fairly large range of emission rates across the models. So in UKSM, we need as much as 100 teragrams per year, but in CSM, we only need about 5. So there's a very large uncertainty in the aerosol forcing that we get across these models. But regardless, when we calibrate the MCB emissions and then we apply them in these simulations, we are able to maintain this 1.5 K target pretty successfully. So when we take a look at the actual temperature patterns we get, so on the top I'm showing the SSP 245 temperature anomalies. In the middle, this is the anomalies in the MCB simulation. So this is greenhouse gases plus MCB, and then on the bottom, this is just taking the MCB signal. And so you can see that, for CSM and UKSM, I've computed the statistics. For E3SM, I only have 1 ensemble member so far. But you can see that there's a significant reduction in the temperature anomalies globally across the 3 models, and there's much fewer significant land temperature changes in CSM2 and E3SM. And then in the case of UKSM, actually, we're not quite cooling enough, especially at northern high latitudes. And then I think as a final point, we wanted to compare MCB and SAI. And so on the left, on the right, I'm showing a comparison of MCB in A, C, and E. This is the same anomalies as before on the previous slide. And then on the far right, these are showing the SAI, equivalent SAI simulations from ARISE. And so you can see that, in general, the precipitation anomalies are fairly similar in the middle row. This mid-latitude MCB scenario is able to produce a temperature response that is a temperature and precipitation response that is broadly more similar to SAI than previously tested MCB scenarios. Mid-latitude MCB is more efficient at cooling and provides a temperature response that is more similar to ARISE SAI. And then there's this large uncertainty in the sea-salt aerosol emission forcing, and so we want to encourage people to do explicitly defined fixed SSD simulations to ensure that we're understanding these uncertainties. Thank you.
We can have one quick question.
I'm wondering about the hemispheric asymmetry, and in particular, since the background aerosol would be so different, would this cloud susceptibility be different, and would you have to account for that, and if your controller does account for that?
So yes, we do find that especially the Southern Ocean regions, the red boxes in the Southern Hemisphere, we do get more forcing per unit mass emission, especially in CSM and E3SM. We do we do try to account for that, but our controller is just one-dimensional. It only accounts for the global mean surface temperature, so we're trying to account for the hemispheric asymmetry by just setting the relative emission rates in the 2 hemispheres. So there's more emissions in the northern mid-latitudes than the southern mid-latitudes.
Okay, thanks.
Thank you. Okay, now let's move on to our session last talk. We'll begin by Irene Isami. She's also going to talk about the marine cloud brightening and impact on seasonality.
Hello, everyone. Thank you for staying for the last talk of the session. So I'll be presenting some work today that I worked on in collaboration with Jack Chen here at NCAR. And it was just accepted for publication with GRL, so if anyone's interested, please scan the QR code to read the paper, but I'll show it again at the end. And I think I can skip this because we just saw it. So previous studies of marine cloud brightening, or MCB, show that while it could reduce surface temperatures, it also commonly results in uneven cooling patterns and a perpetual La Nina-like sea surface temperature response, which was just mentioned. And this is exemplified in the plots shown on the slide here, which really highlight that La Nina-like state. Chen et al. 2024 explore susceptibility-based cloud seeding strategies, finding that by deploying MCB over the 5% of the ocean surface most susceptible to cloud seeding, they get these uneven cooling patterns and La Nina-like state. However, by targeting least susceptible regions over a larger percentage of the ocean, they're able to get a more uniform cooling pattern and also avoid triggering La Nina. They find that the 20% least susceptible scheme is the most uniform impact of the experiments they tested. So these are the cloud seeding masks from Chen et al. 2024, and this study uses monthly varying masks. So the top is for December and the bottom is for June. Note that the 20% scheme largely covers the wintertime mid-latitude regions, whereas the 5% scheme largely covers those tropical and subtropical regions, which is what we want to move away from. So we adapt the 20% scheme into new cloud seeding masks, which also cover 20% of the ocean surface, but over more uniform regions, largely within the mid-latitudes and a single hemisphere at a time. And we simulate MCB with CESM2, fully coupled with 3D ocean and active land and sea ice. And for this project, we don't inject sea salt aerosol, but actually just simulate MCB by artificially increasing the cloud drop number concentration of clouds within the boundary layer to 375 per centimeter cubed within the model grid boxes specified by our cloud seeding masks. And our MCB experiments are initiated in 2035, which is when they branch off of our control experiment, which follows SSP2 4.5. And our target is to restore present day or control 2020 to 2039 temperature and precipitation conditions. So we first started our study with shorter sensitivity experiments testing the deployment of single hemisphere MCB within the months of local winter and summer, which are expected to induce different levels of cooling. And the surface temperature response of our MCB experiments here compared to the present day level suggests that summer seeding leads to a significant amount of cooling, up to 3 degrees Celsius in some regions, but the cooling patterns are non-uniform, largely cooling the seeded hemisphere. And our winter seeding strategies lead to a more uniform impact on temperature, but there is minimal cooling achieved here as the surface temperature response resembles that of SSP2 4.5. And we also consider the impact of our experiments on precipitation rate, specifically focusing on whether or not we shift the ITCZ. So the graphs here just give you an idea of whether or not the ITCZ is shifting north or south. And we find that these summer seeding strategies shift the ITCZ toward the opposite hemisphere MCB is deployed, so shifting toward that warmer hemisphere, whereas the winter seeding strategies do not demonstrate that same shift. And we confirm this with the spatial distribution of precipitation rate response, where we find that the summer seeding strategies lead to changes in precipitation along the equator, where that ITCZ is, whereas the winter seeding strategies lead to little precipitation rate response, which is statistically significant. So the results of our sensitivity experiment suggest the local summer seeding strategies lead to these undesirable side effects, whereas our local winter seeding strategies avoid the side effects, but they don't produce enough cooling. So we create two new scenarios in which we extend MCB into the fall and winter months for 6 months of the year, and we run these simulations from 2035 to 2069, and these are still single hemisphere experiments. So we find the fall plus winter seeding strategies lead to a larger impact on temperature than the local winter only strategies, but the cooling patterns are non-uniform, largely cooling oceanic regions. And we also see that the two strategies here shift the ITCZ, so we deem these strategies not viable for climate intervention. So to avoid these side effects, we combine the fall plus winter schemes into a single scheme in which MCB is deployed for each month of the year and for 6 months of the fall and winter in either hemisphere. And we find the fall plus winter in both hemisphere scheme and 20% least susceptible scheme from Chen et al. 2024 demonstrate a similar performance to one another, both maintaining the present-day global annual average surface temperature and precipitation rate relatively well throughout that 35-year simulation, albeit with slightly more intense cooling from our combined scheme. And we also get a more uniform impact on temperature with the fall plus winter seeding in both hemispheres scheme compared to the other experiments that we tested. And we also avoid shifting the ITCZ. And finally, we consider the impacts of our MCB experiments on the El Niño Southern Oscillation with the Niño 3.4 index. Just for the sake of time, I'm going to look at the sensitivity experiments only here. So the percentages shown on the screen here represent the time spent in La Niña from each of our experiments. So each of the sensitivity experiments lead to an increase in frequency in time spent in La Niña compared to the control for that same time period. However, there is an interesting seasonality aspect to this, especially in the southern hemisphere. We find that the summer seeding strategy within the southern hemisphere triggers a larger impact on ENSO than the winter seeding strategy, whereas for the northern hemisphere, we get a more similar impact from summertime and wintertime seeding. So in conclusion, I just want to highlight that the seasonality of MCB deployment is important for climate outcomes. For instance, it can affect the cooling pattern, shifting the ITCZ and ENSO. And again, there's that preprint link if anyone would like to read the paper. And thank you so much. I'll take any questions.
We can have a couple of questions.
Hi, I'm wondering if like you're focusing instead of the most sensitive, the least sensitive regions. Is there another way that you would pick your regions based on their sensitivity that you think would help like maximize the cooling per area seeded and also reduce the effects? Like, do you need to do the least sensitive regions, or is there another spatial pattern?
I think that study that I referenced, Chen et al. 2024, kind of shows that these least susceptible regions are better at avoiding these undesirable side effects than the other regions that have been largely focused on, like the tropics and the subtropics. Does that answer your question?
Yes, I'm wondering what about the 75% in between? Like, have you looked at how, like, patterns of picking those and what kind of results it would give you?
I haven't looked at that specifically, but in the Chen et al. Paper I mentioned, they explore a couple of different seeding areas, so from like 10 to 40% of the ocean surface. So they do kind of explore some different regions that are being seeded, but the 20% scheme was more uniform in its impact, which is why I based my maps off of those.
Well, thank you.
Thank you.
Nice talk. I'm curious, and maybe from the last MCB talk as well, given the sensitivity to localized regions, do you have a sense of like what the likelihood of transport into a sensitive region might be if these things were deployed, I guess? Does that make sense?
I'm not sure I'm understanding your question.
Yeah, so if like you emit in the mid-latitudes, for example, and you have a tropical cyclone, you could, or some sort of circulation feature that could bring those aerosols or marine cloud brightening compounds into the tropics, right?
I think the idea of the mid-latitudes is to kind of place this along the storm tracks, if I'm remembering correctly, so that it should kind of distribute that cooling from the mid-latitude regions.
Okay, thank you.
Thank you.
All right, now we conclude our session. Let's thank all the speakers and the poster presentators one more time. So after the meeting, if you have any questions or comments, you can send an email to me, Sarah, and Ayla. And if there's any activities currently going on at CVCWG, if you want to participate, just also tell us. Okay? And thank you, and hope you enjoy the rest of the workshop.